The sun burns at 27 million degrees Fahrenheit. Right now, this second. A sphere of nuclear fury so violent it converts 4 million tons of matter into pure energy every single second. The light it releases has been traveling for 8 minutes to reach your eyes. The heat radiating from its surface could vaporize anything humanity has ever built in less time than it takes to blink. And yet, just beyond the thin shell of atmosphere that wraps this planet, the universe sits frozen at 454 degrees below zero. The same temperature it has held for 13.8 billion years. The same temperature it will hold long after every star in the cosmos burns out. This is not a mystery science has ignored. This is a paradox so fundamental that answering it requires dismantling everything you think you know about heat itself. Because heat is not what you were taught, temperature is not what it seems, and the vacuum of space, that black ocean separating every burning star in existence, does not work the way your instincts insist it should. Astronauts orbiting Earth experience 500-degree temperature swings every 90 minutes as they pass between sunlight and shadow. Moons like Europa hold oceans of liquid water beneath crusts of ice, heated by forces that have nothing to do with the sun. And everywhere, in every direction, space itself hums at a temperature left over from the moment the universe exploded into existence, a chill that has never warmed and never will. So why does the vacuum never heat up? Why can the most powerful object in our solar system pump endless fire into the void and leave it untouched? And what does that tell us about the narrow thread of warmth we call home? This is that answer. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The sun is a bomb that never stops exploding. Somewhere around 93 million miles from the chair you are sitting in, a ball of plasma 864,000 miles wide is running a continuous thermonuclear reaction so violent that every second it converts 4 million tons of matter directly into energy, not burning, not combusting. Converting mass into light according to Einstein's equation, the one everyone recognizes but almost nobody understands. At the core, where the furnace actually runs, temperatures reach 27 million degrees Fahrenheit. That number doesn't mean much until you try to find something to compare it to. The surface of the sun, the photosphere, the glowing yellow disk you can see through a telescope, sits at roughly 10,000 degrees Fahrenheit, hot enough to vaporize any known material in a fraction of a second. The core is 2,700 times hotter than that. If you tried to stack comparisons to make the scale comprehensible, you would fail. There is nothing in human experience, nothing in our atmosphere, nothing on Earth that comes within 1,000 degrees of what happens at the center of the sun. And yet, step away from it, not far, just a few million miles. Get yourself out into the space between planets, away from Earth's protective blanket of atmosphere, away from any surface that might hold heat, and the temperature drops to negative 454 degrees Fahrenheit. That is 3 degrees above absolute zero. Absolute zero is the point where atoms stop moving, where thermal motion ceases, where the universe runs out of heat entirely. Space sits just barely above that edge. 3 degrees. That is the difference between the coldest natural temperature in the universe and the background radiation filling the void between stars. So here is the paradox. The most powerful heat source in our solar system, an object radiating energy at a rate of 380 billion watts, sits in the middle of a void so cold it might as well be frozen solid. The sun has been burning for 4, 6 billion years. It has pumped more energy into the space around it than all of human civilization will ever generate if we survive for 1 million years, and the vacuum surrounding it has not warmed by a single degree. Most people, when they first hear this, assume someone made a mistake. The numbers must be wrong, or the measurements are off, or there is some kind of trick in the definitions. There isn't. The sun really is that hot. Space really is that cold. And the two conditions exist simultaneously, right next to each other, separated by nothing but emptiness. If you were standing on Earth and you lit a bonfire, the air around the fire would warm. Walk 10 feet away and you would feel the heat. Walk 100 feet and you might still feel a faint warmth if the wind was right. The heat spreads, it diffuses, it moves outward from the source and raises the temperature of everything nearby. That is what heat does. That is how every fire you have ever experienced behaves. The sun does not work that way. You can be 10 million miles from it and feel nothing, no warmth, no glow, nothing. The vacuum does not carry the heat. It does not warm. It does not transfer the energy in the way air or water or metal would. The sun radiates energy in every direction at the speed of light, but the space that energy travels through remains as cold as it was before the sun existed. That should bother you, because it means something fundamental about heat, about temperature, about the way energy moves through the universe does not work the way your daily experience has trained you to think. Let's be clear about what the sun is doing. At its core, hydrogen nuclei are being crushed together by gravity so intense that it overcomes the electromagnetic repulsion that normally keeps atomic nuclei apart. When two hydrogen nuclei fuse, they form helium, and in that process, a tiny fraction of their combined mass disappears. That missing mass becomes energy, photons, light, heat, radiation. The energy released by a single fusion event is minuscule. The energy released by the sun every second is anything but. Roughly 600 million tons of hydrogen fuse into helium every second. 4 million tons of that mass vanish, converted into pure energy. That energy begins as gamma rays, the most energetic form of light, smashing outward from the core in every direction. But the core is surrounded by layers of plasma so dense that those gamma rays cannot travel more than a fraction of an inch before colliding with another particle. Each collision scatters the photon, changes its direction, saps a bit of its energy. The light bounces again and again, millions of times, slowly working its way outward through 400,000 miles of roiling plasma. The journey from the core to the surface takes roughly 100,000 years. A photon born in a fusion reaction today will not reach the sun's surface until long after every person currently alive has died. By the time it finally escapes, the gamma ray will have been scattered, absorbed, re-emitted and downgraded in energy so many times that it emerges as visible light or infrared radiation, still carrying energy, still moving at the speed of light, but no longer the violent gamma ray it started as. Once free of the photosphere, the light travels unobstructed. 8 minutes and 20 seconds later, it reaches Earth. Some of it hits your skin, some of it strikes a solar panel, some of it warms the ocean, and a tiny fraction of it gets absorbed by a telescope pointed at the sky. That is how we know the sun is there. That is how we know what it is doing. That is how we measure its temperature, its composition, its age, and the reactions happening in its core. We are reading mail that took 100,000 years to write and 8 minutes to deliver. But here is the thing that nobody tells you when they explain how the sun works. That light, that energy, that torrent of radiation pouring out of the sun in every direction at every moment does not heat the space it travels through. It only heats the things it hits. If you put a rock in space a few million miles from the sun, the side facing the sun will heat up. The side facing away will stay frozen. The rock will reach an equilibrium temperature determined by how much energy it absorbs and how much it radiates away, but the vacuum around the rock will not warm. The emptiness between the sun and the rock will remain at -454 degrees. The light passes through without transferring heat to the medium because there is no medium, there is nothing there to heat. This is not a trick of language. This is not a technicality. This is the reality of how heat works, and it runs directly counter to every intuitive lesson your brain has learned from living on a planet with an atmosphere. On Earth, heat spreads. Light a candle in a closed room and the air warms, not just near the candle, everywhere. The air molecules absorb energy, speed up, collide with other molecules and spread the heat around. Convection currents form. Warm air rises, cool air sinks. The whole room reaches a rough equilibrium. You do not need to touch the flame to feel the warmth. The air carries it to you. Space has no air. It has no molecules to carry the heat. It has no medium to conduct, no currents to convect. It has only radiation. And radiation on its own does not raise the temperature of a vacuum. It cannot. Because a vacuum has no temperature, temperature is a measure of the average kinetic energy of particles in a substance. If there are no particles, the concept of temperature stops meaning anything. You can talk about the energy of the photons flying through the void. You can measure their wavelength, their frequency, their momentum, but you cannot assign a temperature to the space they are passing through because there is nothing there to be hot or cold. This is where the paradox lives, not in the sun, not in the space, but in the assumption most people carry around that heat and hot are the same thing. They are not. Heat is energy transfer. Hot is a property of matter. The sun produces heat. Space cannot be hot. They are playing different games on different fields. Here is another way to think about it. Imagine you are floating in space, far from any star, far from any planet. You are wearing a spacesuit, but for the sake of argument, let us say you could survive without it. What would you feel? You would feel cold. Brutally, lethally cold, because your body is made of matter. Your skin, your blood, your cells, all of them contain particles that are moving, vibrating, holding thermal energy. In the vacuum, there is nothing around you to absorb that energy except you. Your body radiates heat as infrared light. That light flies off into the void and never comes back. You cool down, fast. There is no air to hold the warmth close to your skin. No conduction, no convection, just radiation. You would freeze, not because space is cold, but because you are losing heat faster than your body can produce it. Now turn and face a star. Suddenly you are being bombarded by radiation, visible light, ultraviolet, infrared, all of it carrying energy. The side of your body facing the star absorbs that energy and heats up. The side facing away continues radiating into the void and stays cold. You become a temperature gradient, one side baking, one side freezing, and the space around you, the emptiness between you and the star, remains unchanged, still sitting at -454 degrees, still hovering just above absolute zero. Astronauts deal with this every time they go outside the International Space Station. The station orbits in low Earth orbit, roughly 250 miles up, still close enough that Earth's atmosphere provides a tiny bit of drag. But the atmosphere at that altitude is so thin it might as well not be there. For thermal purposes, the astronauts are in vacuum. When they work in sunlight, the suits have to protect them from temperatures exceeding 250 degrees Fahrenheit. When they work in shadow, The suits have to protect them from temperatures dropping below -250 degrees Fahrenheit, a swing of 500 degrees depending on whether they are in the sun's line of sight or not. The suits manage this with layers of insulation, reflective coatings, and active cooling systems that pump heat away from the astronaut's body. It is not elegant, it is barely enough. And it only works because the engineers who designed the suits understood that in space, heat does not spread, it only moves by radiation. You are either absorbing it or you are not. There is no in-between. Back to the sun. The core sits at 27 million degrees. The surface sits at 10,000 degrees. You would think the temperature would drop smoothly as you move outward. Core, interior, surface, space, a steady gradient from hot to cold. It does not. Just above the photosphere, in a region called the corona, the temperature spikes, not by a few hundred degrees, by millions. The corona, the sun's outer atmosphere, the faint halo you can see during a total solar eclipse, reaches temperatures between 1, 8 and 3, 6 million degrees Fahrenheit. Hotter than the surface below it, hotter than the layers closer to the core. That should not be possible. Heat does not flow from cold regions to hot regions. Thermodynamics does not allow it. And yet there it is, a layer of plasma hundreds of times hotter than the surface it sits on top of, floating in the space above the sun like a contradiction wrapped in fire. Scientists have been trying to explain the corona problem for more than 70 years. The current best answer involves magnetic fields. The sun's magnetic field does not sit still. It twists, it kinks, it snaps. When field lines reconnect, they release energy, a lot of energy, enough to accelerate particles to extreme speeds and heat the plasma to millions of degrees. The process is called magnetic reconnection, and it happens constantly all over the sun's surface. Tiny explosions, nanoflares, each one barely detectable on its own, but billions of them happening every second, pumping energy into the corona faster than it can radiate away. That explanation works, mostly. It explains the temperature, it explains the observations, but it also highlights just how strange the sun is. You have a core at 27 million degrees surrounded by a surface at 10,000 degrees, and then an atmosphere at 2 million degrees, and then a vacuum at -454 degrees, all layered on top of each other with no contradiction because the rules governing heat transfer change depending on whether you are in matter or in emptiness. The universe does not care whether the picture makes sense to you. It runs on physics, not intuition. And the physics say that heat only moves in 3 ways: conduction, convection, and radiation. Conduction requires direct contact, molecules vibrating against each other, passing energy along the chain. Space has no molecules. Conduction does not happen. Convection requires a fluid. Hot fluid rises, cool fluid sinks, and the motion carries heat from one place to another. Space has no fluid. Convection does not happen. That leaves radiation, light, photons, electromagnetic waves carrying energy at the speed of light from the source to whatever they eventually hit. Radiation does not need a medium. It works just fine in vacuum, but it also does not warm the vacuum. The photons pass through. They do not interact with the emptiness. They only deposit their energy when they strike something solid, an asteroid, a planet, a spacecraft, you. This is why space stays cold, not because the sun is weak, not because space is far away, but because the emptiness between the sun and everything else has nothing in it to absorb the heat. The energy is there, flooding outward in every direction, but energy in flight is not the same as temperature. Temperature is local, temperature is matter, and space is neither. If you stood on the surface of Mercury, the closest planet to the Sun, daytime temperatures would hit 800 degrees Fahrenheit, hot enough to melt lead, hot enough to make the ground glow faintly red. But step into the shadow of a crater and the temperature would plummet to negative 290 degrees, not gradually, almost instantly. Because there is no atmosphere to hold the heat, no air to carry warmth from the sunlit side to the shadowed side. Just rock, radiation and vacuum. The rock facing the sun absorbs energy and heats up. The rock facing away radiates energy and cools down, and the space around both stays frozen. People hear about the sun's temperature and they imagine space as a warm place, a glowing place. They picture the void between planets as something filled with heat, like the inside of an oven. That picture is wrong. Space is not an oven. It is not even a room. It is the absence of a room. It is the absence of everything. And in the absence of matter, heat has nowhere to go. The sun has been pouring energy into the vacuum for more than 4 billion years. It will keep pouring energy into the vacuum for another 5 billion years until it runs out of hydrogen to fuse and begins the slow collapse into a red giant. And through all of that, the space around it will not warm by a single degree. It will remain at negative 454 degrees, just as it was before the sun ignited, because the vacuum does not absorb heat. It never has, it never will. The paradox is not a flaw in the universe. It is a window, a crack in the intuition we built by living our entire lives surrounded by air and water and solid ground, a clue that the rules we learnt on Earth do not apply everywhere. And the moment you stop expecting space to behave like a room with the heater on, the moment you accept that emptiness is truly empty, the universe stops looking like a contradiction and starts looking like exactly what it is, a place where matter is the exception and void is the rule, where heat is not a blanket that spreads, but a beam that travels, where the coldest natural temperature in existence and the hottest nuclear furnace in the solar system sit side by side, separated by nothing, touching nothing, affecting nothing except the rare clumps of matter that drift between them. That is the reality. That is the cosmos. And if you want to understand why the sun does not warm space, you first have to understand what heat actually is, not the feeling, not the glow, the physics, the motion, the particles. Because the answer is not out there in the void, it is in here, in the nature of matter itself. Heat is not what you think it is. You have spent your entire life feeling heat. You know what it means when something is hot. You know what happens when you touch a stove, when you stand in sunlight, when you hold a cup of coffee. The sensation is immediate, undeniable, and so familiar that you have probably never stopped to ask what heat actually is at the level where physics operates. Most people, if pressed, would say heat is energy. That is true, but incomplete. Heat is not just energy floating around waiting to warm things up. Heat is a very specific kind of energy tied to a very specific kind of motion, and that motion requires something that space by definition does not have. At the smallest scale, matter is made of particles, atoms, molecules. Depending on what you are looking at, those particles might be bonded together in rigid lattices like the steel in a bridge, or flowing past each other like the water in a river, or flying around independently like the air in a room. But no matter what state the matter is in, solid, liquid, or gas, the particles are always moving. Always. Even in a block of ice sitting motionless on a table, the water molecules inside are vibrating, jiggling in place, shaking against the bonds holding them in their crystalline structure. That motion is not optional. It is not something that starts when you heat the ice and stops when you cool it. The motion is what temperature is. Temperature, in the most precise sense, is a measure of the average kinetic energy of the particles in a substance. Kinetic energy is the energy of motion. The faster the particles move, the higher the temperature. The slower they move, the lower the temperature. That is the entire definition. Temperature is not a substance, it is not a fluid, it is not something that flows from one place to another. It is a statistical property of a collection of moving particles. When you heat a pot of water on the stove, you are not pouring heat into the water like you would pour milk into a glass. You are speeding up the water molecules. The burner transfers energy to the metal pot. The metal atoms start vibrating faster. Those vibrations get passed to the water molecules at the bottom of the pot. The water molecules collide with each other, spreading the motion upward through the liquid. The average speed of all the molecules increases, and we call that increased temperature. This is not a metaphor. This is not an analogy. This is what heat is. The kinetic energy of particles in motion. If you remove the particles, you remove the motion. If you remove the motion, you remove the heat. And if you remove the heat, the concept of temperature stops making sense. Space is not empty in the way a jar with no water in it is empty. Space is empty in a way that is difficult to describe because there is no human scale analogy that captures it. The vacuum of space is not a container with nothing inside. It is the absence of container and contents both. It is a region where matter, on average, does not exist. In low Earth orbit, the region where the International Space Station flies, there are still a few stray atoms drifting around. Hydrogen mostly, helium, trace amounts of oxygen and nitrogen that have leaked out of Earth's atmosphere. The density is roughly 1 million atoms per cubic centimeter. That sounds like a lot until you compare it to the air you are breathing right now, which contains about 10 to the power of 19 molecules per cubic centimeter. The vacuum at the altitude of the space station is 10 trillion times less dense than air at sea level. Go farther out, past the moon, past the orbit of Mars, into the deep void between planets, and the density drops even lower. In interstellar space, the average is about 1 atom per cubic centimeter. In the intergalactic voids, the vast dark regions between galaxy clusters, the density drops to 1 atom per cubic meter or less. At that point, calling it matter is generous. It is more accurate to call it a rounding error. And here is the problem. If temperature is the average kinetic energy of particles, and there are no particles, then there is no average. You cannot take the mean of an empty set. You cannot measure the speed of motion when there is nothing moving. The question, what is the temperature of space, is not a question with a difficult answer. It is a question that does not pass. This is not a technicality. This is the core of why space does not warm up, no matter how much energy the sun pours into it. The energy is there. It is real. It is measurable. But energy in the form of light flying through a vacuum does not interact with the vacuum in a way that raises its temperature because the vacuum has no temperature to raise. Let's talk about how heat moves, because this is where intuition breaks down completely. There are 3 ways to transfer thermal energy from one place to another: conduction, convection, and radiation. Every instance of heating or cooling you have ever experienced in your life falls into one of these 3 categories. Understanding the difference between them is the only way to make sense of why the sun can be surrounded by a furnace at its core and a freezer in the void outside. Conduction is the simplest. It is heat transfer by direct contact. Put a metal spoon in a cup of hot coffee and the handle warms up. The heat is not climbing up the spoon like water up a straw. What is happening is that the atoms in the part of the spoon touching the coffee are vibrating faster because the coffee molecules are hitting them. Those fast vibrating atoms bump into the atoms next to them, making them vibrate faster. those atoms bump into the next layer, and so on, passing the kinetic energy up the handle one collision at a time. Metals are good conductors because their atoms are packed tightly together and they have free electrons that can carry energy efficiently. Wood is a bad conductor because its structure is full of air pockets and the atoms are not arranged in a way that lets them pass energy quickly. But both wood and metal conduct some amount of heat as long as there is matter present to do the bumping. In a vacuum there is no matter. There are no atoms to bump into each other. Conduction does not happen, not slowly, not inefficiently, not at all. Convection is heat transfer by the motion of a fluid. Boil water in a pot and you will see convection in action. The water at the bottom heats up, becomes less dense and rises. The cooler water at the top sinks to replace it. The whole pot starts circulating. That circulation spreads heat throughout the liquid faster than conduction alone ever could. The same thing happens in the atmosphere. Air warmed by the ground rises. Cooler air sinks. Wind is just convection happening on a planetary scale. Hurricanes, thunderstorms, the gentle breeze on a spring afternoon, all of it driven by the fact that hot air is less dense than cold air, and fluids in a gravitational field do not sit still when there is a density difference. Convection requires a fluid, gas or liquid, something that can flow. Space has no fluid. There is no air to rise, no water to circulate. Convection does not happen, not weakly, not at all. That leaves radiation. Radiation is heat transfer by electromagnetic waves, light, in the broad sense. Visible light, infrared, ultraviolet, radio waves, microwaves, X-rays, gamma rays, all of them are the same phenomenon, just at different wavelengths. And all of them carry energy. When you stand in front of a fire, most of the heat you feel is not coming from hot air blowing toward you. It is coming from infrared radiation emitted by the flames and the glowing coals. That radiation travels through the air, hits your skin, gets absorbed, and the energy converts into the kinetic motion of the molecules in your skin. You warm up. Radiation does not need a medium. It works in air. It works in water. It works in solid rock. And critically, it works in vacuum. Light does not care whether there is matter in the way. Photons are their own thing, and they travel at the speed of light, regardless of what they are moving through or not moving through. This is the only way heat escapes the sun. The core generates energy through fusion. That energy works its way to the surface by radiation and convection through the plasma layers inside the sun. Once it reaches the photosphere and escapes into space, conduction and convection stop. There is no more matter dense enough to conduct. There is no more fluid to convect. The energy continues outward purely as radiation, photons flying through the void at 186,000 miles per second. Those photons do not heat the space they travel through because there is nothing in the space to heat. They only deposit their energy when they hit something solid, a planet, a moon, a spacecraft, a speck of dust. At that moment, the photon gets absorbed, its energy converts into the kinetic motion of the atoms in the object, and the object warms up. But the vacuum itself, the emptiness between the sun and the object, remains cold. Not because the photons are not there, they are, trillions of them passing through every square inch of space every second, but because the photons do not interact with the vacuum in a way that raises its temperature, they are just passing through. Think of it this way. Imagine you are standing in a dark room holding a flashlight. You turn it on and point it at the far wall. The light travels from the flashlight to the wall. Does the air between the flashlight and the wall get brighter? No. The air is invisible. The light passes through it without illuminating it. You only see the light when it hits something. The wall, a speck of dust, your hand. heat works the same way in space. The radiation is there traveling through the void, but the void does not light up and it does not warm up. It just lets the radiation pass. Now let's talk about what happens when you actually put matter into space, because that is where the numbers start to look insane. Take a rock, any rock, place it in orbit around the Sun at the same distance as Earth, about 93 million miles out. One side of the rock faces the Sun, the other side faces away. What happens? The side facing the Sun gets hammered by radiation. Photons carrying energy slam into the surface, get absorbed by the atoms in the rock, and those atoms start moving faster. The surface heats up. Depending on the rock's color, its composition, and how reflective it is, the sunlit side might reach 250 degrees Fahrenheit or higher. The side facing away from the Sun does not receive any direct sunlight. It does not get hit by photons, so it does not heat up from radiation, but it is still made of atoms, and those atoms are still moving, which means it still has thermal energy. That energy radiates away as infrared light. The dark side cools down. Depending on how well the rock conducts heat internally, the shadowed side might drop to negative 250 degrees or lower. The rock reaches an equilibrium. Energy in from the Sun on one side, energy out as radiation on all sides. The temperature stabilizes at whatever value balances the two. For an object at Earth's distance from the Sun with no atmosphere and no internal heat source, that equilibrium temperature is around 0 degrees Fahrenheit, give or take depending on the details. The important part is this: the rock has a temperature. The vacuum around the rock does not. The rock is made of particles. The particles are moving. That motion is temperature. The vacuum is not made of particles. There is no motion. There is no temperature. You can measure the rock's temperature with a thermometer. You cannot measure the vacuum's temperature because the vacuum does not have one. You can measure the energy of the photons flying through the vacuum. You can calculate the equivalent temperature those photons would produce if they were absorbed by a perfect blackbody. But that is not the same as the vacuum having a temperature. That is the temperature of the radiation field, not the temperature of space itself. Astronauts have to deal with this every time they go outside. A spacesuit is not designed to keep you warm the way a winter coat keeps you warm. A winter coat works by trapping a layer of air next to your skin. Your body heats that air, and the coat keeps it from blowing away. Convection is blocked. Conduction is minimized. You stay warm because the heat stays close. In space, there is no air to trap. A puffy coat would do nothing. The vacuum does not conduct heat away from you, but it also does not hold heat near you. Your body generates heat, roughly 100 watts, the same as a bright incandescent light bulb. That heat has to go somewhere. In a vacuum, the only way out is radiation. Your body emits infrared light. That light flies off into space. You cool down. At the same time, if you are in sunlight, you are being blasted by solar radiation. The Sun delivers about 1,400 watts of energy per square meter at Earth's distance. An average human body has a surface area of roughly 2 square meters. If you were floating in space with no protection, the sunlit side of your body would absorb close to 1,400 watts, while the shadowed side radiated away 100 watts. You would not freeze, you would cook. A spacesuit handles this with layers. The outer layer is coated with materials that reflect most of the sun's energy. Underneath, there are layers of insulation that slow the transfer of heat from the outside to the inside. And inside, there is a liquid cooling garment, basically a tight-fitting suit with tubes running through it, that circulate cold water to pull heat away from the astronaut's body. The water gets pumped to a radiator on the back of the suit where it radiates the heat into space as infrared light. It is an active system. It has to be. Because in space you cannot rely on the environment to regulate your temperature. The environment does not have a temperature. Here is another way to think about the strangeness of it. If you are floating in the vacuum and you want to get warm, you cannot rub your hands together and expect the friction to help much. Friction generates heat by increasing the kinetic energy of the molecules at the surface where two objects slide past each other. That works fine on Earth because the heat spreads into the surrounding air and into your hands by conduction and convection. In space, the heat you generate at the point of friction stays there. It does not spread efficiently because there is no air to carry it. The surfaces in contact get hot. Everything else stays cold. The same principle explains why spacecraft have such a hard time managing heat. Electronics generate heat. Solar panels generate heat. Humans generate heat. All of that energy has to leave the spacecraft somehow, or the interior will keep getting hotter until something breaks. On Earth, you cool electronics with fans, blow air over the hot components, and convection carries the heat away. In space, fans are useless. There is no air to blow. The only option is radiation. Spacecraft have radiators, large flat panels designed to emit infrared light into space. The bigger the radiator, the more heat you can dump. The International Space Station has enormous radiator arrays, bright white panels stretching out from the main structure like wings. Those panels are not solar panels, they are coolers. Without them, the station would overheat in hours. The vacuum does not care. It does not absorb the heat. It does not warm up. It just lets the infrared light pass through, carrying the energy away into the void where it spreads outward forever, diluting into the background radiation of the universe. Now think about what this means for the Sun. The Sun has been radiating energy into space for more than 4 billion years. Every second, it converts 4 million tons of matter into energy. Every second, that energy leaves the Sun as light, traveling outward in all directions. Some of it hits planets, most of it does not. Most of it flies off into the interstellar medium, spreading outward until it is so diluted that no instrument could ever detect it. And the space that energy passes through does not warm, not by a degree, not by a fraction of a degree, because space is not made of matter. It does not have particles to speed up. It does not have atoms to absorb the photons. It is empty, and empty things do not have temperature. This is the point where the human brain starts to rebel because it does not match experience. You have never encountered a situation where heat flows through a region without warming the region. On Earth, that does not happen. Heat a room and the air warms. Heat a lake and the water warms. Heat a rock and the rock warms. The idea that energy can flood through a space without changing the space feels wrong. It is not wrong, it is just unfamiliar. And the reason it is unfamiliar is that you have never lived in a place without matter. You have spent your entire life surrounded by atoms. Air, water, ground, walls, other people, all of it matter, all of it capable of having temperature, all of it capable of absorbing and releasing heat. Space is not like that. Space is the exception to every rule you learned growing up. It is the place where heat transfer loses 2 of its 3 mechanisms and temperature stops being a meaningful concept unless there is an object present to assign it to. Which brings us to the final piece of the puzzle. If radiation is the only way heat moves through space, and radiation does not warm the vacuum, then how does the sun's energy reach Earth? How does it warm the planet? How does life exist on a rock 93 million miles away from the nearest furnace, separated by a void so cold it sits just above absolute zero? The answer is not complicated, but it requires letting go of the idea that heat spreads like a blanket. Heat does not spread, energy does, and energy, when it is carried by light, travels in straight lines at the speed of light until it hits something. The sun radiates energy. Earth intercepts a tiny fraction of that energy. The energy gets absorbed. The molecules in the atmosphere and the oceans and the ground speed up. The planet warms. The vacuum between the sun and Earth does not participate. It does not warm. It does not cool. It simply allows the light to pass, unchanged, uninterrupted, cold as it has always been, because temperature is a property of matter and space is the absence of matter. That is the truth at the heart of the paradox. Heat is not a thing that fills space. Heat is motion. Motion requires particles. Particles are rare. Space is common. And the most powerful furnace in the solar system sits in the middle of the coldest natural environment in the universe, not because of a flaw or a contradiction, but because the rules governing heat transfer do not apply when there is nothing to transfer heat to. The sun is not reaching out to touch us, not in the way you might imagine. There is no stream of hot gas flowing through space like water through a pipe. There is no glowing trail of heat spreading outward from the photosphere to Earth. There is no mechanism by which the sun's core temperature of 27 million degrees could conduct itself across 93 million miles of emptiness and arrive here as a pleasant 70-degree afternoon. What the sun is doing instead is broadcasting. Not sound, not signals. Energy, pure energy in the form of light. And that light, traveling at 186,000 miles per second, carries everything the sun has to give. This is thermal radiation, the third and final method of heat transfer, the only one that works in a vacuum, the only reason anything in space can exchange energy at all. Radiation is not a backup plan. It is not a weak substitute for conduction and convection. It is the primary way energy moves through the universe. Every star, every planet, every object with a temperature above absolute zero emits radiation. Right now, your body is radiating infrared light. The screen you are looking at is radiating. The walls around you are radiating. Everything with thermal energy is constantly broadcasting that energy outward as electromagnetic waves. You do not notice it because the amount of energy your body radiates is small, and the air around you is also radiating, and the two are in rough equilibrium. But the radiation is happening. It never stops. It is as fundamental to the nature of matter as mass or charge. Here is how it works. Every atom, every molecule, every charged particle in the universe is constantly jiggling, moving, vibrating, and when a charged particle accelerates, which includes changing direction even if the speed stays constant, it generates an electromagnetic wave, a photon, a ripple in the electromagnetic field that travels outward at the speed of light. The hotter an object is, the faster its particles are moving. The faster they are moving, the more they accelerate. The more they accelerate, the more photons they emit. And crucially, the higher the temperature, the shorter the wavelength of the emitted photons. This is not a metaphor. This is not something that kind of works this way if you squint. This is a law of physics. It is called Planck's law, and it describes exactly how much radiation an object emits at every wavelength based on its temperature. A human body at 98.6 degrees Fahrenheit emits most of its radiation in the infrared at wavelengths around 10 micrometers. You cannot see it, but an infrared camera can. That is how thermal imaging works. It is not detecting heat in some vague sense. It is detecting the photons your body is emitting because your skin is warm. A piece of metal heated to 1000 degrees Fahrenheit starts to glow red, not because something is being added to the metal, but because at that temperature, the metal is emitting enough visible light in the red part of the spectrum that your eyes can see it. Heat it hotter and it glows orange, then yellow, then white. The color tells you the temperature. The sun's surface, at 10,000 degrees Fahrenheit, emits most of its radiation in the visible spectrum. That is not a coincidence. That is why the sun looks bright. That is why we can see it. The photosphere is hot enough that the light it radiates falls into the narrow band of wavelengths our eyes evolved to detect. The core, at 27 million degrees, emits gamma rays. The corona, at 2 to 3 million degrees, emits X-rays and extreme ultraviolet light. But by the time the energy from the core works its way to the surface, scattered and reabsorbed and re-emitted thousands of times, it has been downshifted into visible light and infrared. The sun is a blackbody radiator, and like all blackbody radiators, its spectrum is determined entirely by its temperature. Every second, the sun radiates 380 billion watts of power. That is 380 followed by 24 zeros. Written out, it is 380 septillion watts. In scientific terms, 8 times 10 to the 26th watts. The number is incomprehensible on a human scale. For context, the total energy consumption of all human civilization, every power plant, every car, every light bulb, every smartphone, adds up to about 18 trillion watts. The sun radiates 20 million times more energy every second than humanity has used in the entire span of recorded history, and it does this by turning mass into light. 4 million tons of mass per second, converted into photons via Einstein's equation, the one everyone recognizes, E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is a very large number. Squaring it makes it enormous, which means even a tiny amount of mass converts into a staggering amount of energy. In the core, hydrogen nuclei are fusing into helium. 4 hydrogen nuclei combine to make one helium nucleus. The helium nucleus weighs slightly less than the 4 hydrogens that went into it. That missing mass, about 0.7% of the original, becomes energy. Photons, light, heat, radiation. Those photons begin their journey as gamma rays, the most energetic form of light, with wavelengths shorter than the diameter of an atomic nucleus. But the core is surrounded by 400,000 miles of dense plasma. The gamma rays cannot travel more than a fraction of an inch before colliding with another particle. Each collision scatters the photon, changes its direction, and slightly reduces its energy. The photon bounces, again and again, millions of times, billions of times. The journey from the core to the surface is not a straight line. It is a random walk, a drunkard stumble through the densest material in the solar system, and it takes time, a long time. Current estimates suggest a photon born in the core will take somewhere between 100,000 and 170,000 years to reach the surface. Not because it is moving slowly. Photons always travel at the speed of light. But because the path is so convoluted, with so many collisions and redirections, that the effective outward progress is glacial. By the time the photon finally escapes the photosphere, it has been scattered so many times and lost so much energy that it is no longer a gamma ray. It emerges as visible light or infrared radiation, still carrying energy, still traveling at 186,000 miles per second. But no longer the violent high-energy particle it started as. Once free of the sun, the photon flies through space unobstructed. No more collisions, no more scattering, just open void. 8 minutes later, it reaches Earth. Some photons hit the atmosphere and get absorbed or scattered by air molecules. Some make it all the way to the ground, and a tiny fraction of them hit your skin. When that happens, the photon's energy gets absorbed by the molecules in your skin. The molecules speed up. You feel warmth. That is not the photon warming the space between the sun and you. That is the photon transferring its energy to your body upon impact. The vacuum the photon traveled through remains as cold as it was before the sun ignited. This is the key point that most explanations gloss over. Radiation is not heat moving through space. Radiation is energy moving through space. Heat only appears when the energy interacts with matter. People use the word heat loosely. They say the sun heats the earth. They say radiation carries heat. But heat, in the strict thermodynamic sense, is energy transfer due to a temperature difference. Heat is what happens when energy moves from a hot object to a cold object. The photon itself is not hot. It does not have a temperature. It is a packet of energy, a quantum of electromagnetic radiation. It only becomes heat when it gets absorbed by something capable of having temperature. Think of it this way. A bullet fired from a gun carries kinetic energy. It flies through the air without warming the air. The air does not care that the bullet is passing through it at high speed. The bullet only deposits its energy when it hits something. At that moment, the kinetic energy converts into other forms: heat, deformation, sound. But while the bullet is in flight, the energy is in transit. It has not transferred yet. Photons work the same way. They carry energy through space. The space does not warm up. The energy stays locked inside the photon until the photon hits something and gets absorbed. At that instant, the energy transfers. The object warms. The photon ceases to exist. Mission accomplished. The sun emits photons in all directions, spherically, uniformly. Every point on the surface radiates outward into the surrounding void. Most of those photons never hit anything. They fly off into interstellar space, spreading outward until they are so diluted and redshifted by the expansion of the universe that they become undetectable. Earth intercepts a tiny fraction of the total. If you imagine the sun at the center of a sphere with a radius of 93 million miles, Earth's cross-sectional area covers about 1/2 billionth of that sphere's surface. So for every 2 billion photons the sun emits, Earth catches one. The rest fly past. That one photon, though, is enough, because the sun is emitting so many photons that even a 2 billionth share amounts to an enormous flux of energy. At Earth's distance, the sun delivers about 1,400 watts of power per square meter. That number is called the solar constant, though it is not perfectly constant. It varies slightly with the sun's activity cycle and with Earth's elliptical orbit. But on average, every square meter of surface facing the sun receives 1,400 watts. For comparison, a typical space heater outputs 1,500 watts. So standing in direct sunlight on a clear day is roughly equivalent to standing in front of a space heater, except the heater is 93 million miles away and the warmth is arriving as light. That light does not warm the vacuum it passes through. It only warms the things it hits. Earth's atmosphere absorbs some of it. The ground absorbs some of it. The oceans absorb some of it. Each photon that gets absorbed transfers its energy to the molecules in the absorbing material. Those molecules speed up. The material warms. That warmth spreads through conduction and convection, but only after the initial absorption happens. Without the sun's radiation, Earth would be a frozen ball. The atmosphere would condense into liquid nitrogen and oxygen pooled at the poles. The oceans would freeze solid. The surface temperature would drop to near absolute zero within days. The only heat left would be the faint trickle of geothermal energy leaking out from the planet's core, and that would not be nearly enough to keep anything alive. Radiation is not just one way energy moves through space. It is the only way, and the speed at which it moves is fixed. Light travels at 299,792,458 meters per second in vacuum. That is not an average, that is not a maximum under ideal conditions. That is the speed, always, everywhere, for every photon. The distance from the Sun to Earth is 93 million miles. Convert that to meters and you get 149.6 million kilometers, or about 149.6 billion meters. Divide that by the speed of light and you get 499 seconds, 8 minutes and 19 seconds. That is how long it takes for a photon leaving the Sun's surface to reach Earth. Not the core, the surface. The energy in the photon may have been born in a fusion reaction 100,000 years ago, but the photon itself, the one carrying that energy to Earth, was emitted from the photosphere 8 minutes ago. This creates a strange situation. When you look at the Sun, you are not seeing it as it is right now. You are seeing it as it was 8 minutes ago. If the Sun suddenly vanished, you would not know for 8 minutes. The light that left the Sun before it vanished would still be on its way, and Earth would continue to receive sunlight and warmth for 8 more minutes before the sky went dark and the temperature began to drop. The same delay applies in reverse. If something happens on Earth, the Sun would not know for 8 minutes. Not that the Sun knows anything, but in terms of information transfer, there is no way for a signal to travel faster than light. 8 minutes is the shortest possible time for anything, information, energy or matter, to cross the gap between the Sun and Earth. Light does not experience time the way we do. From the photon's perspective, if photons had perspectives, the journey is instantaneous. Time dilation at the speed of light compresses the travel time to zero. A photon emitted from the Sun and absorbed by your retina experiences no time between emission and absorption. It exists, from its own frame of reference, for 0 seconds. That is not a useful way to think about it, though, because photons do not have clocks. The 8-minute travel time is what matters to us. The stationary observers watching the light move through space. And the light does move. It does not teleport. It does not jump. It propagates through the electromagnetic field at a fixed speed, carrying its energy along like a ripple moving across the surface of a pond. The ripple is not the water moving forward. The water just goes up and down. The ripple is the pattern moving forward. A photon is similar. It is a disturbance in the electromagnetic field, a wave packet traveling outward from the source. When the photon hits Earth's atmosphere, several things can happen. Some photons get scattered by air molecules, which is why the sky is blue. Blue light has a shorter wavelength than red light, and shorter wavelengths scatter more easily. The Sun emits white light, which is a mix of all visible wavelengths. But when that light enters the atmosphere, the blue gets scattered in all directions. That is what you see when you look up. Not the Sun's light directly, but the scattered blue light bouncing around the atmosphere. Some photons get absorbed by water vapor, carbon dioxide, and ozone. These molecules are good at absorbing specific wavelengths, particularly in the infrared and ultraviolet. The absorbed energy heats the atmosphere. That is where some of the greenhouse effect comes from. The Sun's energy enters as visible light, gets absorbed by the ground, re-emitted as infrared, and then trapped by greenhouse gases in the atmosphere that absorb infrared better than visible light. Some photons make it all the way to the surface. When they hit the ground, they get absorbed by the molecules in the soil or the pavement or the ocean. The molecules vibrate faster, the surface warms. That warmth conducts downward into the ground and upward into the air. Convection takes over, and the atmosphere starts to circulate. Weather happens, life happens. all because photons from the sun transferred their energy to matter. Radiation is extraordinarily efficient at long distances because it does not rely on a medium. Conduction and convection are powerful, but they are limited by how fast energy can diffuse through matter. Radiation is limited only by the speed of light, and the speed of light is absurdly fast. If the sun were to suddenly double its energy output, we would not feel the change for 8 minutes. If the sun's core shut down completely, the surface would keep radiating for thousands of years because the energy stored in the outer layers would take that long to leak away. The sun is not a light bulb that turns on and off instantly. It is a massive reservoir of thermal energy that changes slowly over time scales measured in millions of years. The photons we see today were emitted from the surface 8 minutes ago, but the energy in those photons was generated in the core tens of thousands of years ago. The light carries information about the sun's surface temperature, its composition, and its activity level, but it does not tell us what is happening in the core right now. For that, we need neutrinos, the ghostly particles produced in fusion reactions that pass through the sun's outer layers without interacting and reach Earth in about 8 minutes. Neutrinos give us real-time data on the core. Photons give us delayed data on the surface. Here is another strange consequence of radiation being the only heat transfer mechanism in space. If you take two objects and place them near each other in a vacuum, they will eventually come to thermal equilibrium, but it will take a very long time, much longer than it would in air or water. On Earth, if you put a hot object next to a cold object, the air between them conducts and convects heat from the hot side to the cold side. Equilibrium happens in minutes or seconds. In space, the only transfer mechanism is radiation. The hot object radiates infrared light. Some of that light hits the cold object and gets absorbed. The cold object warms up. The hot object radiates more than the cold object, so over time the hot object cools and the cold object warms until they are both radiating the same amount. At that point, they have reached equilibrium. But the process is slow because only the photons that happen to travel in the direction of the other object contribute to the transfer. Most of the radiation flies off into space and never returns. The efficiency is low, the time required is long. This is why spacecraft designers have to think very carefully about thermal management. You cannot rely on the environment to cool your electronics quickly. You have to actively radiate the heat away using large surface areas designed to maximize infrared emission. The sun does not have this problem. The sun radiates so much energy that it does not care whether the radiation gets absorbed or not. The radiation is leaving the surface at a rate of 380 billion watts. That energy has to go somewhere. It spreads outward, diluting with distance according to the inverse square law. The inverse square law says that the intensity of radiation decreases with the square of the distance from the source. Double the distance and the intensity drops to 1/4. Triple the distance and the intensity drops to 1/9. By the time the sun's radiation reaches Earth, it has spread over a sphere with a surface area 93 million miles in radius. The intensity at Earth is much lower than at the sun's surface, but it is still 1,400 watts per square meter, enough to power a planet. Go farther out and the intensity continues to drop. At Mars, the solar constant is about 590 watts per square meter. At Jupiter, it is 50 watts per square meter. At Neptune, it is about 1.5 watts per square meter. The sun's energy is still reaching those planets, but the flux is so low that surfaces in sunlight barely warm above the background temperature of space. And yet, even at Neptune, 30 times farther from the sun than Earth, the vacuum between the sun and the planet does not warm. The photons are still flying through space at the speed of light, still carrying energy, still obeying the inverse square law, but the vacuum itself remains at negative 454 degrees because the vacuum has nothing to warm. This is why space-based telescopes are so effective. There is no atmosphere to distort the light. There is no air to scatter the photons. The light from distant stars travels through the vacuum for millions or billions of years and arrives at the telescope essentially unchanged. A photon that left a star 10 billion light-years away and entered the James Webb Space Telescope last week has been traveling through space for 10 billion years, passing through voids and galaxy clusters and clouds of gas, and it still carries the information it started with. The wavelength may have been stretched by the expansion of the universe, but the photon itself has not decayed or degraded. It just kept moving. Radiation is the universe's postal service. It delivers messages across distances that would be impossible to cross by any other means, and it does so at the maximum possible speed, carrying energy and information bundled together in packets of light. Without radiation, the universe would be a very different place. Stars would still fuse hydrogen into helium, but the energy would be trapped inside. Planets would freeze. Life would be impossible. The only reason Earth is habitable is that the sun radiates energy. That energy travels through 93 million miles of vacuum, and that vacuum allows the light to pass without absorbing it or warming up or interfering in any way. The sun's embrace is not a hug, it is a broadcast. A constant stream of photons, flying outward at the speed of light, indifferent to the vacuum they pass through, carrying the energy that powers every living thing on this planet. And when those photons arrive, when they slam into the molecules in your skin or the pavement or the leaves of a tree, the energy transfers, the molecules speed up, warmth appears, but the journey is cold. The space between the sun and Earth is as frozen as the space between galaxies. The radiation does not warm it. The radiation just passes through, 8 minutes at the speed of light, from the surface of a star to the surface of a planet, bridging the void with nothing but energy and time. And on the other end of that journey, standing in the sunlight, you feel warmth. Not because the space around you is warm, but because the photons that traveled 93 million miles in silence have finally found something to hit. Standing on Earth, temperature is something you take for granted. Step outside and you know within a few seconds whether you need a jacket. The air tells you, your skin tells you. The feedback is immediate, predictable, and reliable. Hot days feel hot. Cold days feel cold. The transitions are gradual. Morning warms into afternoon. Evening cools into night. Nothing about the process feels dangerous unless you are caught unprepared, and even then you have time to react. In orbit, temperature stops being a convenience and becomes a threat, not a distant theoretical threat, an immediate, constant, life-or-death engineering problem that every spacecraft and every astronaut has to solve every minute of every day. The International Space Station orbits Earth at an altitude of roughly 250 miles, moving at 17,500 miles per hour. It completes one full orbit every 90 minutes. That means every 45 minutes, the station passes from direct sunlight into Earth's shadow and then back into sunlight again. Sunrise every 45 minutes, sunset every 45 minutes, 16 sunrises and 16 sunsets in a single 24-hour period. Each time the station enters sunlight, the temperature of any surface facing the sun spikes to around 250 degrees Fahrenheit, sometimes higher depending on the angle and the material. Each time the station enters Earth's shadow, the temperature of that same surface plummets to around negative 250 degrees Fahrenheit, sometimes lower. That is a swing of 500 degrees in 45 minutes. 16 times a day, every day. Nothing on Earth behaves like that. Not deserts, not polar ice caps, not the inside of a parked car on a summer afternoon. Nowhere on this planet will you encounter a 500-degree temperature swing in under an hour, repeating endlessly with no atmosphere to cushion the extremes. The vacuum does not care. The vacuum does not moderate. It does not hold heat. It does not spread heat. It just sits there, perfectly indifferent, while objects inside it absorb radiation from the sun on one side and radiate their own heat into the void on the other. This creates problems that most people never think about because most people do not spend time in environments where the rules of heat transfer have been reduced to a single mechanism. On Earth, if you get too hot, you step into the shade. The air in the shade is cooler. Your body conducts heat into the air. Sweat evaporates. Convection carries the heat away. You cool down. In space, stepping into the shade does not help the way you think it should. The shade is not cooler in the sense that there is cool air waiting there. The shade is just the absence of direct sunlight. You stop absorbing radiation from the sun, but you are still radiating your own heat into the vacuum. And because there is no air to conduct heat away from your body, and no convection to carry it off, the only thing regulating your temperature is how much infrared light your suit or your spacecraft can emit. If you are in sunlight, you are absorbing roughly 1,400 watts of power per square meter. That is the solar constant at Earth's distance. A human body in a spacesuit has a surface area of about 2 square meters. If you were standing in direct sunlight with no protection, the sun would be delivering close to 2,800 watts of energy to your body. For reference, a typical household space heater outputs 1,500 watts. You would be absorbing nearly twice that much, and you would have no way to get rid of it except by radiating it back out as infrared light. Your body generates about 100 watts of heat just by being alive. Metabolism, muscle activity, brain function, all of it produces waste heat. On Earth, that heat dissipates into the air easily. In space, it does not. It stays inside your suit unless the suit has a mechanism to remove it. Add 2,800 watts from the sun and 100 watts from your body, and you are looking at a total heat load of 2,900 watts. Your body cannot handle that, not for long. You would overheat in minutes. Step into shadow and the situation reverses. Now you are not absorbing 2,800 watts from the sun. You are only generating 100 watts internally, and you are radiating heat into a void that sits at negative 454 degrees Fahrenheit. You are a warm object in the coldest natural environment in the universe, and the only thing preventing you from freezing is the insulation in your suit and the heat your body continues to produce. But 100 watts is not much. If the suit does not trap that heat efficiently, you will cool down fast, dangerously fast. The astronauts who go outside the station to perform spacewalks, what NASA calls extravehicular activities or EVAs, are dealing with this problem the entire time they are out there. The suit is not just keeping them alive by providing air. It is keeping them alive by managing a thermal environment that would kill them in minutes if the systems failed. A modern spacesuit, the kind used on the ISS, is called an extravehicular mobility unit, or EMU. It weighs about 280 pounds on Earth, though in orbit it has no weight. It is made of 14 layers of material, each one serving a specific purpose. Some layers provide structure, some provide pressure, some provide micrometeorite protection, and several layers, the ones closest to the outside, are designed specifically to manage heat. The outermost layer is white, not for aesthetics. White reflects most of the visible light that hits it. The sun's energy arrives mostly as visible light and near infrared. A white surface reflects 85 to 90% of that energy. The rest gets absorbed. That small percentage is still a lot of energy, but it is manageable. A black surface, by contrast, would absorb most of the incoming energy and heat up much faster. Early spacecraft and suits were often painted white or covered in reflective materials for exactly this reason. Underneath the white outer layer, there are multiple layers of aluminized mylar, a thin plastic film coated with aluminum. These layers act as radiant barriers. They reflect infrared light. When the suit or the spacecraft starts to warm up from absorbed sunlight, the interior surfaces begin radiating infrared. The aluminized layers reflect that radiation back inward, preventing it from escaping too quickly. This keeps the temperature inside more stable. But reflection and insulation are passive systems. They help, but they are not enough on their own. The suit also needs active cooling. That is where the liquid cooling and ventilation garment comes in. Astronauts call it the LCVG, or more commonly, the cooling suit. The LCVG is a tight-fitting garment made of spandex with plastic tubes woven into the fabric. The tubes run all over the astronaut's body, covering the torso, arms, and legs. Cold water circulates through the tubes, absorbing heat directly from the astronaut's skin. The water gets pumped to a device called a sublimator, located in the backpack of the EMU. The sublimator is one of the most elegant pieces of engineering in the entire suit. It works by exposing the warm water to the vacuum of space through a porous plate. In vacuum, water does not boil the way it does on Earth. It sublimates. It goes directly from liquid to vapor without passing through a rolling boil. The phase change absorbs a huge amount of energy, cooling the remaining water dramatically. The cooled water then circulates back through the tubes in the LCVG, pulling heat away from the astronaut's body. The process repeats continuously for as long as the astronaut is outside. The sublimator can remove several hundred watts of heat, which is enough to keep the astronaut comfortable even in direct sunlight. Without the LCVG, an astronaut in sunlight would overheat in less than 10 minutes. The suit would trap the heat, and the astronaut's core temperature would rise until heat exhaustion or heat stroke set in. With the LCVG, an astronaut can work outside for 6 or 7 hours without overheating, as long as the water supply lasts. In shadow, the cooling system can be dialed back. The astronaut is no longer absorbing 2,800 watts from the sun, so the thermal load drops. The suit's insulation is good enough to keep the astronaut warm in shadow as long as the body is still generating its 100 watts of metabolic heat. But if the astronaut stops moving, stops working, the heat generation drops and the suit can start to feel cold. Astronauts have reported that during long EVAs, especially when they are waiting in shadow for a task to be set up, they can feel a chill even with the suit's insulation. The station itself faces the same thermal challenges, just on a much larger scale. The ISS is enormous. It is about the size of a football field, with modules, trusses, solar panels, and radiators extending in all directions. Some parts of the station are in sunlight, some parts are in shadow. And because the station is rotating relative to the sun as it orbits, different parts cycle through sunlight and shadow on different schedules. The solar panels, for instance, are always pointed toward the sun. They track the sun as the station orbits, rotating on joints to keep the panels perpendicular to the incoming light. That maximizes power generation, but it also means the panels are constantly absorbing heat. Solar panels are not perfectly efficient. A typical panel on the ISS converts about 14% of the incoming sunlight into electricity. The other 86% becomes heat. That heat has to go somewhere. The panels are designed to radiate heat efficiently. They are thin, with large surface areas, and they have high emissivity. Emissivity is a measure of how well a surface radiates infrared light. A perfect blackbody has an emissivity of 1. Most real materials have emissivities between 0.8 and 0.95. The ISS solar panels are on the higher end of that range, which means they radiate heat effectively and do not overheat even in direct sunlight. Inside the station, the situation is different. The modules are pressurized. They are full of air, equipment, and people. All of that generates heat. The computers, the life support systems, the lights, the experiments, the astronauts themselves, all of it produces waste heat. On Earth, that heat would dissipate into the surrounding environment through the walls, through ventilation, through open windows. In space, the heat has nowhere to go except out through the walls by radiation. But the walls of the ISS are insulated. They have to be, or the interior would lose heat too quickly in shadow. The insulation is multi-layer, similar to the spacesuit, with reflective barriers that trap infrared radiation. That is great for keeping the interior warm in shadow, but it also means the heat generated inside the station does not escape easily. It builds up. To manage this, the ISS has radiators, lots of them. The radiators are large, flat panels, bright white, mounted on the station's truss structure. They are positioned so that they face away from the sun and away from Earth, looking out into deep space. The radiators are connected to the station's internal cooling system by loops of ammonia, a fluid that is very good at carrying heat. Ammonia circulates through the station's modules, absorbing heat from the air and the equipment. The hot ammonia is pumped out to the radiators. The radiators emit the heat as infrared light into the vacuum. The ammonia cools down and gets pumped back inside. The loop runs continuously 24 hours a day, removing several kilowatts of waste heat. Without the radiators, the interior of the ISS would overheat within hours. The temperature would climb until the equipment started failing and the astronauts became dangerously uncomfortable. The radiators are not optional, they are critical, and they work entirely by radiation. There is no air to blow across them, no water to dump the heat into. Just large surfaces with high emissivity radiating infrared light into the void. The radiators are also vulnerable. They are exposed to space, which means they can be hit by micrometeoroids or space debris. A puncture in a radiator panel does not cause an explosive decompression like it would in a pressurized module, but it does cause a leak in the ammonia loop. Ammonia is toxic, and losing it means losing cooling capacity. The station has backup systems and redundant loops, but a major radiator failure would be a serious problem. In 2007, during a spacewalk, astronauts noticed a small tear in one of the station's solar arrays. The tear was not causing an immediate problem, but it was growing, and there was concern that it could eventually affect power generation. The repair was tricky because the array was under tension, and any mistake could make the tear worse. The astronauts used a makeshift tool, essentially a long pole with clips, to stabilize the array while they applied a patch. The whole operation took place in sunlight, and the astronauts were acutely aware that the array they were working on was hot. Not hot enough to burn through the suit, but hot enough that they had to be careful where they placed their hands. That is one of the strange things about working in space. You can be touching a surface that is 250 degrees Fahrenheit, and as long as the contact is brief and the suit's insulation is intact, you do not feel the heat. The suit does not conduct heat well, which is exactly the point. But it also means you cannot rely on your sense of touch to tell you if something is dangerously hot. You have to trust the instruments and the procedures. Chris Hadfield, the Canadian astronaut who commanded the ISS in 2013, described the thermal environment during EVAs as one of the most disorienting aspects of spacewalks. He said you can have one arm in direct sunlight, baking, and the other arm in shadow, freezing, and your brain has a hard time making sense of the contradiction. On Earth, your body expects the environment to be uniform, hot or cold, not both at once. In space, uniformity does not exist. You are a thermal gradient, and you have to learn to ignore the signals your body is sending because they do not match the reality. Material properties matter enormously in space. Two objects sitting side by side in the same sunlight can reach wildly different temperatures depending on their surface properties. A piece of aluminium with a polished surface will stay cooler than a piece of aluminium with a rough black coating, even though they are made of the same material. The difference is absorptivity and emissivity. Absorptivity is how much of the incoming radiation an object absorbs. A white surface has low absorptivity, maybe 0, 1 or 0, 2, meaning it absorbs 10 to 20% of the incoming light and reflects the rest. A black surface has high absorptivity, close to 0, 9 or 1, meaning it absorbs almost all the incoming light. Emissivity is how much infrared radiation an object emits. A shiny metal surface has low emissivity, maybe 0, 1 or 0, 2, meaning it does not radiate heat well. A rough black surface has high emissivity, close to 0, 9 or 1, meaning it radiates heat very effectively. The ideal material for staying cool in sunlight has low absorptivity and high emissivity. It reflects incoming visible light and radiates infrared efficiently. White paint is a classic example. It absorbs little sunlight and emits infrared well. That is why most spacecraft are painted white or covered in white thermal blankets. The worst material for staying cool has high absorptivity and low emissivity. It absorbs a lot of sunlight and does not radiate heat well. Polished aluminum, ironically, is a terrible choice for surfaces exposed to the sun. It absorbs more than you would think because it is metallic and it does not emit infrared efficiently. So it heats up and stays hot. Gold, on the other hand, has very low emissivity but also low absorptivity in certain wavelengths. That is why you see gold foil on many spacecraft. The gold reflects infrared radiation extremely well, which makes it useful as a radiant barrier in multi-layer insulation. But it is not used on outer surfaces exposed to direct sunlight because it would absorb too much visible light. It is used in layers underneath, where its job is to reflect infrared back inward and keep the interior warm. Engineering a spacecraft or a spacesuit is an exercise in balancing these properties. You want to reflect as much sunlight as possible to avoid overheating. You want to radiate as much heat as possible when you do absorb energy. And you want to insulate the interior so that heat does not leak out too quickly in shadow. All of this has to be done with materials that can survive temperature swings of 500 degrees, micrometeorite impacts, atomic oxygen erosion, and years of exposure to ultraviolet radiation. The materials degrade over time. The white paint on the ISS, for example, starts out bright and highly reflective. After a few years in space, it yellows and becomes less reflective. The absorptivity increases. The surfaces start absorbing more heat. Engineers have to account for this in their thermal models. They design the systems to work not just when the materials are new, but when they are old and degraded. Astronauts doing spacewalks have to be aware of their own thermal state constantly. They wear sensors inside the suit that monitor their core temperature and their skin temperature. If the cooling system is not keeping up, the sensors will alert them and they have to reduce their activity level or return to the airlock. Overheating in a spacesuit is not like overheating on a hot day. There is no shade to step into, no breeze to cool you down. The suit is your environment, and if the suit cannot cool you, you are in serious trouble. There have been close calls. In 2013, Italian astronaut Luca Parmitano was performing a spacewalk when his helmet started filling with water. The water was coming from the cooling system. A blockage in the sublimator had caused water to back up into the ventilation loop, and it was leaking into his helmet. Within minutes, there was enough water in the helmet that it was covering his eyes, nose, and ears. He could not see. He could barely breathe. He had to navigate back to the airlock by memory, following the safety tethers while effectively blind. The water was cold. In any other context, that might have been a relief, but in a spacesuit, cold water in your helmet is a nightmare. It blocks your vision, it gets in your airway, and it conducts heat away from your head much faster than air would. Parmitano made it back to the airlock, and the crew inside got his helmet off before he drowned. The incident led to a redesign of the sublimator and additional safeguards to prevent water from entering the ventilation system. That incident had nothing to do with the thermal extremes of space directly, but it highlights how fragile the systems are that keep astronauts alive in that environment. The suit has to manage pressure, temperature, oxygen, carbon dioxide removal, and hydration all at once, in an environment that is trying to kill you in a dozen different ways. The thermal challenge is just one of them, but it is constant and unrelenting. The ISS orbits in what is called low Earth orbit, but even at 250 miles up, the environment is not truly empty. There are still a few stray atoms of atmosphere, mostly hydrogen and helium. The density is so low that it might as well be vacuum, but it is not quite, and that tiny bit of residual atmosphere causes drag. Not much, but enough that the station loses altitude slowly over time. Every few months, the station has to fire its thrusters to boost itself back up to a higher orbit. That drag also generates a tiny amount of heat. When the station is moving at 17,500 miles per hour and it collides with even a few atoms, there is friction. Kinetic energy converts into thermal energy. The amount of heat is minuscule, less than a watt, but it is there. The leading surfaces of the station, the ones pointed in the direction of travel, absorb that heat. It is not enough to matter for thermal management, but it is measurable. At higher altitudes, in geostationary orbit or beyond, the drag disappears completely. The environment is true vacuum, but the thermal challenges remain. In fact, they get worse in some ways because there is no Earth to provide a warm backdrop. The ISS benefits from the fact that when it is in shadow, it is in Earth's shadow, and Earth itself is radiating infrared light. That light warms the side of the station facing Earth slightly. It is not much, but it is better than nothing. A spacecraft in deep space, far from any planet, does not have that advantage. It is surrounded by the cosmic microwave background, which sits at -454 degrees Fahrenheit, and the only sources of heat are the sun, which gets dimmer with distance, and the spacecraft's own internal systems. Managing heat in that environment is even harder because the only way to get rid of waste heat is to radiate it, and the colder the radiator, the less efficiently it radiates. This is one of the major challenges for missions to the outer solar system. Spacecraft like Voyager and New Horizons had to be designed to operate in an environment where sunlight is so weak that solar panels are useless. They use radioisotope thermoelectric generators, essentially nuclear batteries, which generate heat from the decay of plutonium. That heat keeps the electronics warm and also gets converted into a small amount of electricity. But even with an internal heat source, the spacecraft still have to manage heat carefully. Too much heat and the electronics overheat. Too little and they freeze. The radiators have to be sized just right, and the insulation has to be thick enough to keep the interior stable, but not so thick that it traps too much heat. The same principles apply to spacesuits, space stations, satellites, and anything else humans build to operate in the vacuum. The vacuum does not warm, the vacuum does not cool, the vacuum does nothing. It is the objects inside the vacuum that have to manage their own thermal state, using only radiation as the transfer mechanism. This is why thermal control is one of the first things engineers think about when designing a spacecraft. It is not an afterthought. It is not something you can fix with a patch or a software update. It is baked into the structure, the materials, the shape, and the orientation of every surface. Get it wrong, and the spacecraft will fail. Get it right, and the spacecraft can operate for years, decades even, cycling through temperature extremes that would destroy any structure on Earth. Astronauts train for this. They spend time in thermal vacuum chambers, large sealed rooms where the air is pumped out and the temperature is controlled with heaters and liquid nitrogen cooling. They practice working in suits, while the chamber cycles through hot and cold extremes. They learn to recognize the signs of overheating and overcooling. They learn to trust the suit's systems, even when their body is telling them something feels wrong. Because in space, your intuition about temperature is worse than useless. It is actively misleading. Your skin is not a reliable sensor. Your sense of hot and cold is calibrated for an environment with air, where heat moves by conduction and convection, where temperature gradients are smooth and predictable. None of that applies in orbit. In orbit, you are either in the sun or you are not. You are either absorbing 1,400 watts per square meter, or you are radiating into a void at negative 454 degrees. There is no in-between. There is no gradual transition. The line between sunlight and shadow is sharp, and crossing it means flipping from one extreme thermal state to another in seconds. And the vacuum does not care. It does not warm to meet you halfway. It does not provide a buffer. It just sits there, empty and indifferent, while you manage your own survival with coatings, insulation, radiators, and cooling systems that have to work perfectly every time, or you die. That is the reality of working in space, and it is the reality every astronaut accepts the moment they step outside the airlock. The sun is there, brilliant and deadly. The void is there, frozen and infinite. And between them, the only thing keeping you alive is a suit full of engineering and a cooling system that has to keep running, no matter what. The universe does not compromise. It does not meet you halfway. And nowhere is that more obvious than in orbit, where the coldest and hottest extremes sit side by side, separated by nothing but the width of a shadow. That is what space does. It strips away the cushion. It removes the middle ground, and it forces you to confront the raw physics of heat transfer with no atmosphere to hide behind. Just radiation, just you, just the sun and the void, and the line between the two is as thin as light itself. Space is not empty. That is the first thing you need to understand before we go any further. You have been lied to. Not maliciously, not intentionally, but lied to nonetheless by every picture of space you have ever seen, every science textbook diagram showing stars scattered across a black void, every movie where spacecraft fly through silent darkness between planets. All of it gives you the impression that space is nothing, a blank canvas, a vacuum in the truest sense of the word. It is not. Space is filled with light, old light, the oldest light in the universe. Light that has been traveling for more than 13 billion years, light that was emitted when the universe itself was an infant, light that carries a message from a time before stars existed, before galaxies formed, before anything we recognize as structure had assembled itself out of the primordial chaos. That light is everywhere. Right now, as you read this, you are being bathed in it. It is passing through your body at the speed of light, trillions of photons every second, completely undetectable to your eyes because your eyes were not built to see microwaves. This light is called the cosmic microwave background, and it is the reason we know the universe had a beginning. It is the reason we can say with confidence that 13.8 billion years ago, everything that exists today was compressed into a region smaller than an atom, hotter than anything we can currently produce in a laboratory, and expanding faster than the speed of light. The CMB is not a theory. It is not a model. It is a measurement, a direct observation of the universe as it existed 380,000 years after the Big Bang. And it tells us, among other things, that the baseline temperature of space, the background hum of the universe itself, sits at -454.8 degrees Fahrenheit. That is 725 Kelvin. That is 7 degrees above absolute zero, the coldest temperature physically possible. The astronauts in orbit experience temperature extremes because they are near the sun. Step into sunlight and you absorb 1,400 watts per square meter. Step into shadow and you radiate into a void that gives nothing back. But the void is not truly empty, and it is not truly 0 Kelvin. It is 7 Kelvin. The difference between 7 and 0 might sound trivial. It is not. Absolute zero is the point where atomic motion ceases entirely. At 7 Kelvin, there is still motion, faint motion, quantum motion, but motion nonetheless. And that motion is being driven by the faint glow of the Big Bang, still washing over everything, 13.8 billion years later. Here is how we found it. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey. They were trying to measure radio signals from the Milky Way using a large horn-shaped antenna that had been built for satellite communications. The antenna was sensitive, and they were looking for faint signals, so they needed to eliminate every possible source of noise. They pointed the antenna at different parts of the sky, expecting to see variation. Some directions should be louder, some quieter, depending on where the radio sources in the galaxy were located. What they found instead was a persistent hiss. No matter where they pointed the antenna, the hiss was there. Same intensity, same frequency. It did not change with time of day. It did not change with season. It did not matter if they were looking at the galactic center or at empty space far from any stars. The hiss was everywhere, uniform, unchanging. Penzias and Wilson assumed it was noise from the equipment. They checked the electronics, they checked the wiring, they checked the antenna itself, and then, famously, they discovered that pigeons had been nesting inside the horn. Pigeon droppings were coating the interior. Maybe that was the problem. They cleaned out the droppings. They shooed away the pigeons. They ran the measurements again. The hiss was still there, exactly as loud as before, exactly as uniform. They were stumped. They had eliminated every terrestrial source they could think of. The signal was coming from space, but it was not coming from any particular direction. It was coming from everywhere at once. That should not be possible unless the entire universe was glowing faintly at microwave frequencies. At the same time, about 30 miles away at Princeton University, a physicist named Robert Dicke and his team were building their own radio telescope. They were building it specifically to search for the cosmic microwave background, not because they had seen it, because they had predicted it. The prediction dated back to the late 1940s. George Gamow, Ralph Alpha, and Robert Herman, working on the early Big Bang model, realized that if the universe had started as a hot, dense state and had been expanding and cooling ever since, there should be leftover radiation from that early hot phase. The universe in its infancy was too hot for atoms to exist. It was a plasma, a soup of protons, electrons, and photons, all colliding constantly. The photons could not travel far before hitting something. The universe was opaque. As the universe expanded, it cooled. Eventually, about 380,000 years after the Big Bang, the temperature dropped low enough that protons and electrons could combine to form neutral hydrogen atoms. This moment is called recombination. It is a misleading name because the protons and electrons had never been combined before, but the term stuck. At recombination, the photons that had been trapped in the plasma were suddenly free to travel. The universe became transparent. The light from that moment, the first light that could travel freely through space, has been traveling ever since. Gamow and his colleagues calculated that the universe at recombination had a temperature of about 3000 Kelvin, hot enough to glow. The light emitted at that temperature would have been visible light and infrared, the kind of glow you see from a piece of heated metal. But the universe has been expanding for 13.8 billion years since then. As space expands, the wavelengths of light traveling through it get stretched. This is redshift, the same phenomenon that makes distant galaxies look redder than they should. The light from recombination has been redshifted so much that it is no longer visible or infrared. It is now in the microwave part of the spectrum, with wavelengths of about 1 millimeter. Alpha and Herman, working in 1948, predicted that this relic radiation should have a temperature of about 5 Kelvin. The prediction was published, noted, and largely ignored for nearly 2 decades. By the early 1960s, Dicke had independently arrived at the same conclusion and was preparing to search for the signal. Then he heard about Penzias and Wilson's mysterious hiss. He realized immediately what they had found. The two groups met. The interpretation was clear. The hiss was not noise. It was the echo of the Big Bang. Penzias and Wilson published their detection in 1965. Dicke's group published the theoretical interpretation alongside it. The two papers together provided the first direct evidence that the universe had a hot, dense beginning and had been cooling ever since. The discovery was so significant that Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, not for proposing the Big Bang, for detecting the leftover light from it. The cosmic microwave background is not a faint signal hidden among brighter sources. It is the dominant source of electromagnetic radiation in the universe. There are roughly 400 cMb photons in every cubic centimeter of space. Compare that to the density of atoms, which averages about 1 atom per cubic centimeter in interstellar space. The universe contains 400 times more cMb photons than atoms. The vacuum is not empty. It is glowing. You cannot see the glow because your eyes do not detect microwaves. But if you could tune your vision to the right frequency, the entire sky would be glowing faintly, uniformly, in every direction. No stars, no galaxies, just a smooth, even light filling every corner of the universe. That light is the cMb. That glow is the universe's temperature. And that temperature is 725 Kelvin. Here is what that number means. Temperature, as we have established, is the average kinetic energy of particles. In a vacuum with no particles, temperature does not make sense as a concept. But space is not a true vacuum. It is filled with cMb photons. Those photons carry energy. You can assign a temperature to a field of radiation by asking, what temperature would a black body need to have to emit radiation with this spectrum? The CMB has a nearly perfect blackbody spectrum, which means it looks exactly like the radiation emitted by an object at 725 Kelvin. That is the universe's temperature, not the temperature of a particular object or region. The temperature of the radiation field filling all of space. When you step into the shadow of the International Space Station and your suit radiates heat into the void is not at 0 Kelvin, it is at 7 Kelvin. The difference is negligible for most engineering purposes. Your suit is radiating infrared light at wavelengths around 10 micrometers. The CMB is arriving at wavelengths around 1 millimeter. The two do not interact strongly. The CMB does not warm your suit in any meaningful way because the flux of energy is so low, but the CMB is there, always, everywhere, a faint background hum that never goes away. The uniformity of the CMB is one of its most striking features. When Penzias and Wilson measured it, they found the same temperature in every direction to within their instruments' precision. Subsequent measurements with better instruments confirmed this. The CMB is isotropic, uniform, the same temperature everywhere to about 1 part in 100,000. That uniformity tells us that the early universe at the time of recombination was extraordinarily smooth. There were tiny fluctuations, density differences of about 1 part in 100,000, but on average, every region of the observable universe had the same temperature and density. This smoothness is both a confirmation of the Big Bang model and a puzzle. It confirms the model because a hot, dense beginning naturally produces a uniform radiation field, but it is a puzzle because the universe today is not smooth. Galaxies, stars, planets, all of these are clumps. Structure. The universe went from nearly perfect uniformity 380,000 years after the Big Bang to the highly structured cosmos we see today. How did that happen? The answer lies in those tiny fluctuations. 1 part in 100,000 does not sound like much, but it was enough. The regions that were slightly denser than average had slightly stronger gravity. They pulled in more matter. As they grew, their gravity grew stronger, and they pulled in even more matter. Over hundreds of millions of years, those tiny density differences grew into the seeds of galaxies. The first stars formed inside the densest regions. Those stars exploded, seeding the surrounding gas with heavy elements. New stars formed from the enriched gas. Galaxies assembled, clusters formed. And all of it started from fluctuations in the CMB so small that they were not detected until 1992. That detection came from a satellite called the Cosmic Background Explorer, or COBE, launched by NASA in 1989. COBE was the first spacecraft designed specifically to study the CMB. It carried 2 main instruments. One measured the spectrum of the CMB to see if it really was a perfect blackbody. The other measured the temperature of the CMB in different directions to search for the tiny fluctuations predicted by theory. In 1990, COBE's spectrum instrument called Pheros announced its first results. The CMB had the most perfect blackbody spectrum ever measured. The data matched the theoretical curve so precisely that when the results were presented at a scientific conference, the audience gave a standing ovation. A standing ovation for a graph. That is how important the result was. It confirmed, beyond any remaining doubt, that the CMB was thermal radiation from a hot, dense, early universe. Every competing theory, every alternative explanation for the universe's origin was effectively ruled out by that single measurement. 2 years later, in 1992, COBE's temperature instrument, called DMR, announced the detection of fluctuations in the CMB. The temperature variations were about 30 millionths of a Kelvin, tiny, but they were there and they were real. The early universe was not perfectly smooth. It had structure, and that structure was the seed of everything we see today. George Smoot, the lead scientist on COBE's DMR instrument, famously said at the press conference announcing the result, "If you are religious, it is like looking at the face of God." The comment was hyperbolic, but the sentiment was not unwarranted. The fluctuations in the CMB are the oldest observable structures in the universe. They are the fingerprints of quantum fluctuations in the first fraction of a second after the Big Bang, stretched to cosmic scales by inflation and imprinted on the radiation field at recombination. Looking at the CMB is looking at the universe in its infancy. It is the earliest snapshot we can ever take. COBE's measurements were revolutionary, but they were coarse. The satellite could only resolve fluctuations on large angular scales. It saw the big picture, but not the details. 2 follow-up missions refined the measurements. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped the CMB with much higher resolution. It measured the fluctuations at scales down to about 1/10 of a degree on the sky. The Planck satellite, launched by the European Space Agency in 2009, went even further, mapping the CMB at even higher resolution and with greater sensitivity. Planck's final results, released in 2018, are the most precise measurements of the CMB ever made. The satellite measured the temperature of the CMB to be 7,255 Kelvin, with an uncertainty of less than 1/1000th of a degree. It mapped the fluctuations across the entire sky with a resolution of about 5 arc-minutes, roughly 1/10 the diameter of the full moon. The data from Planck has been used to constrain the age of the universe, the density of matter and dark matter, the rate of expansion, and dozens of other cosmological parameters. The CMB is not just evidence for the Big Bang, it is the most important dataset in all of cosmology. And it is cold. That is the key point for this chapter. The CMB is not just a relic, it is a temperature. It is the baseline thermal state of the universe. If you could remove the sun, remove all the stars, remove every source of heat in the cosmos, what would be left is the CMB, a uniform glow at 2.7 Kelvin, filling every cubic centimeter of space, carrying the faint warmth of a universe that was once unimaginably hot and has been cooling for nearly 14 billion years. That cooling is a direct consequence of expansion. The universe is not static, it is not sitting still. It is expanding, and it has been expanding since the moment it began. As space expands, the energy density of the CMB decreases. The photons get redshifted to longer wavelengths, which means lower energy. The temperature drops. When the CMB was emitted, the universe had a temperature of about 3000 Kelvin. Today it is 2.7 Kelvin. In the far future, trillions of years from now, the temperature will be even lower, asymptotically approaching zero but never quite reaching it. This is why space is so cold, not because it is empty, because it is filled with radiation that has been redshifted and diluted by 13.8 billion years of expansion. The CMB is the universe's memory of its own beginning, and that memory is fading, slowly, inevitably. The universe is cooling down, and there is nothing that can stop it. The CMB also provides a reference frame for motion. One of the strange consequences of the CMB's uniformity is that you can measure your velocity relative to it. If you are moving through space, the CMB in the direction you are moving toward will appear slightly hotter due to Doppler shift. The CMB in the direction you are moving away from will appear slightly cooler. By measuring this temperature difference, you can calculate your velocity relative to the CMB rest frame. Earth is not stationary relative to the CMB. The solar system is moving, the Milky Way is moving, and our local group of galaxies is moving. When you add up all those motions, Earth is moving through the CMB rest frame at about 370 kilometers per second, roughly 230 miles per second, in the direction of the constellation Crater. That motion creates a dipole pattern in the CMB. One hemisphere of the sky looks slightly warmer, about 3 millikelvin warmer. The opposite hemisphere looks slightly cooler. That dipole is the largest feature in the CMB sky, and it is entirely due to our motion through the universe. Subtract out the dipole and you are left with the intrinsic fluctuations, the seeds of galaxies, the fingerprints of inflation, the structure that grew into everything we see today. Those fluctuations are tiny, but they are the most important signal in the entire universe. They tell us where galaxies came from. They tell us what the universe is made of. They tell us how fast the universe is expanding and how old it is. They are the Rosetta Stone of cosmology, and all of it is written in light. Cold light, ancient light, light that has been traveling for longer than stars have existed, longer than galaxies have existed, longer than the Earth or the Sun or anything familiar. That light is here, right now, passing through you, 400 photons per cubic centimeter, carrying the story of the universe's birth. You cannot feel it, you cannot see it, but instruments can. Radio telescopes pointed at the sky, tuned to microwave frequencies, detect the CMB easily. It is the brightest thing in the microwave sky. Brighter than any galaxy, brighter than any star, brighter than anything except the Sun and a few planets when they happen to be in the beam. The CMB is not hiding, it is not buried under other signals, it is everywhere, loud and clear, if you have the right kind of ears, and it is cold. That is the bottom line. The universe has a temperature, and that temperature is 7 Kelvin. Not 0, not negative 454 exactly. Negative 454, 8. Close enough to absolute zero that the difference barely matters for most purposes, but far enough above it that the universe is not dead. There is still energy, still motion, still light. Faint light, stretched and redshifted beyond recognition, but light nonetheless. This is the baseline. This is the background. This is what space is when you strip away the sun, the stars, the galaxies, and everything else that generates heat. What you are left with is the CMB, a faint glow, a whisper of a universe that was once so hot that matter could not exist. And that whisper is the coldest natural temperature in the universe. It is colder than anything on Earth. It is colder than the coldest winter night in Antarctica. It is colder than liquid nitrogen, colder than liquid hydrogen, colder than liquid helium. The only way to reach temperatures lower than the CMB is to build a laboratory, pump out all the air, shield out all the radiation, and use lasers or magnetic fields to cool atoms down to a few billionths of a Kelvin. And even then, you are only colder than the CMB locally in a tiny controlled environment. The universe itself, the background state of all space, sits at 7 Kelvin. And it will stay there, slowly cooling, for trillions of years. That coldness is not the absence of something, it is the presence of something very specific, the CMB. The echo of the Big Bang, the light that has been traveling since the universe was 380,000 years old. That light is why space is cold. Not because space is empty. Because space is full of ancient radiation that has been redshifted into the microwave band and diluted by cosmic expansion into a faint uniform glow. The sun warms planets, stars warm their surroundings. Black holes, quasars, galaxies, all of them pump energy into the universe. But the baseline, the background, the default state of space when nothing else is nearby, is the CMB. And the CMB is cold. colder than anything you will ever experience outside of a laboratory, colder than the shadowed side of the moon, colder than interstellar space far from any star. It is the coldest thing there is, and it is everywhere. But cold, as it turns out, is not the same as dead. The universe is not a frozen wasteland. It is full of energy, full of motion, full of structure, and some of that structure is warm, not from stars, not from sunlight, but from the inside, from processes that have nothing to do with the sun or the CMB or the radiation filling the space between galaxies. Heat can come from within. It can be generated by forces that have been running since the solar system formed, forces that keep oceans liquid beneath miles of ice, forces that make frozen moons into some of the most interesting places in the cosmos. The CMB is the baseline, but the baseline is not the whole story, and sometimes the most surprising warmth is found in the coldest places. Europa does not look like a place where life should exist. Nothing about it suggests warmth or welcome or the kind of environment where anything could survive for more than a few seconds. The surface temperature hovers around -260 degrees Fahrenheit. The entire moon is smaller than Earth's own moon, just over 1,900 miles across, locked in a perpetual stare at Jupiter, the same hemisphere always facing the giant planet like a soldier at attention. From orbit, Europa looks like a cracked egg, a smooth shell of water ice marked by long reddish-brown streaks and ridges that crisscross the surface for thousands of miles. No mountains to speak of, no craters, just ice, old ice, young ice, fractured ice, ice that has been melted and refrozen and shattered and smoothed over again and again by forces nobody fully understands. And beneath that ice there is an ocean. Not a frozen ocean, not a hypothetical ocean, a liquid ocean. An ocean that contains 2 to 3 times more water than every ocean on Earth combined, sealed under a crust of ice that could be anywhere from 10 to 25 kilometers thick. An ocean that has been liquid for billions of years, never freezing, never exposed to sunlight, never touched by the sun's warmth, sitting in the coldest region of the solar system where the sun delivers barely 50 watts per square meter and the background temperature of space is 7 Kelvin. And that ocean is not just sitting there cold and dead, it is warm, not hot, not boiling, but warm enough to stay liquid. Warm enough that scientists consider it one of the most promising places in the entire solar system to search for life. How does a moon 484 million miles from the sun, 5 times farther from the sun than Earth, stay warm enough to maintain a global ocean beneath miles of ice? The answer has nothing to do with the sun. It has nothing to do with radiation from stars or the cosmic microwave background or any external heat source. The answer is inside. The warmth comes from the inside, generated by a mechanism so powerful and so relentless that it has been running for more than 4 billion years and shows no sign of stopping. The mechanism is called tidal heating, and it is the reason Europa might be the most important moon in the solar system. Jupiter is enormous, the largest planet in the solar system by a wide margin, with a mass more than twice that of all the other planets combined. It has a gravitational pull strong enough to tear comets apart and fling asteroids across the solar system. Europa orbits Jupiter at a distance of about 417,000 miles, completing one orbit every 3-5 days. That orbit is not circular, it is slightly elliptical, nudged into that shape by gravitational interactions with the other large moons, particularly Io and Ganymede. As Europa moves closer to Jupiter and then farther away during each orbit, Jupiter's gravity squeezes and stretches the moon's interior like a rubber ball being flexed in a giant's hand. The squeezing and stretching generate friction. Deep inside Europa, the rocky mantle and the ice shell are being kneaded by tidal forces. Rock grinds against rock. Ice flexes and cracks. The friction generates heat. Not a lot of heat by terrestrial standards. Estimates suggest tidal heating generates somewhere between 1 and 10 trillion watts of power inside Europa. For comparison, Earth's internal heat flow from radioactive decay and leftover primordial heat is about 47 trillion watts. Europa is smaller and less active geologically, but the heat is there, and crucially, it is concentrated in the right places. Near the boundary between the rocky mantle and the ice shell, exactly where it needs to be to keep an ocean liquid. Tidal heating is not unique to Europa. Io, the innermost of Jupiter's large moons, experiences tidal forces so extreme that it is the most volcanically active body in the solar system. Io's surface is constantly being reshaped by eruptions, lava flows and plumes of sulfur dioxide venting into space. The entire moon is being turned inside out by tidal heating. Europa's tidal forces are weaker because it orbits farther from Jupiter and because its orbit is less eccentric, but they are strong enough to melt the interior and keep an ocean liquid for billions of years. We have known Europa had an ocean since the late 1990s, when NASA's Galileo spacecraft made repeated flybys of the moon and measured disruptions in Jupiter's magnetic field near Europa that could only be explained by a vast body of electrically conductive liquid beneath the surface, salt water. The ocean had to be salty because pure water is not conductive enough to produce the magnetic signature Galileo detected. The ocean had to be global because the signal was consistent no matter where the spacecraft flew. And the ocean had to be in contact with a rocky seafloor because the salt had to come from somewhere, and the most likely source is minerals leached from the mantle. The ice shell above the ocean is not static. It is moving, shifting, cracking, refreezing. Some regions of the surface are smooth and ancient, marked by relatively few features. Other regions, particularly the so-called chaos terrains, are jumbled messes of ice blocks that have been tilted, rotated and refrozen at odd angles. The most famous of these regions is Terra Regio, a reddish area on Europa's trailing hemisphere where the ice looks like it has been broken apart and reassembled like a jigsaw puzzle. Terra Regio is geologically young. The lack of craters suggests the surface there is less than 100 million years old, possibly much younger. Something is refreshing the surface. Something is bringing material from below and depositing it on top. The leading explanation is that warm ice or liquid water from the ocean is rising through the ice shell, softening the surface and allowing the ice to collapse and refreeze in a disordered state. This is where the James Webb Space Telescope comes in. In September 2023, two independent research teams published results from Webb's observations of Europa. They were looking for carbon dioxide, and they found it concentrated in Terra Regio, not scattered randomly across the surface the way you would expect if the carbon dioxide came from meteorite impacts or radiation processing. Concentrated, localized, sitting in exactly the kind of terrain that models predict would be refreshed by material welling up from below. The carbon dioxide was not delivered from space. It came from inside. From the ocean. That means the ocean contains dissolved carbon dioxide, which means the ocean has carbon chemistry, which means one of the 4 ingredients necessary for life as we understand it is present. Liquid water, check. Energy, check. Carbon, check. The 4th ingredient is time, and Europa has had plenty of that. The ocean is estimated to have existed for at least 4 billion years, possibly longer. 4 billion years is more than enough time for chemistry to get interesting. Webb also confirmed the presence of water vapor in Europa's thin atmosphere, supporting earlier observations from the Hubble Space Telescope that suggested Europa was venting plumes of water into space. The plumes are not constant like the geysers on Enceladus, Saturn's tiny icy moon, which fires jets of water continuously from its south pole. Europa's plumes appear to be sporadic, possibly triggered by tidal stresses that crack the ice and allow pressurized water to escape. If the plumes are real, and the evidence is now strong enough that most scientists believe they are, then Europa is giving us free samples of its ocean. No drilling required. Just fly through the plume with the right instruments and catch the droplets. That is exactly what NASA's Europa Clipper spacecraft is designed to do. Launched in October 2024, Clipper is on its way to Jupiter and will arrive in 2030. It will not land on Europa. It will not orbit Europa. Jupiter's radiation environment is so intense that parking a spacecraft at Europa would fry its electronics within weeks. Instead, Clipper will orbit Jupiter and make 49 close flybys of Europa, some passing within just 25 kilometers of the surface. During those flybys, Clipper will map the ice shell in detail, measure its thickness using ice-penetrating radar, search for active plumes, analyze the composition of any ejected material, and probe the ocean's depth and salinity using magnetometry. Clipper carries 9 scientific instruments. One of them, called SUDA, the Surface Dust Analyzer, is designed to catch and analyze microscopic grains of ice and dust ejected from Europa's surface by micrometeorite impacts or plume activity. Each grain is a tiny frozen sample of whatever material sits on or just below the surface. SUDA can determine the molecular composition of individual grains. If there are organic molecules in the ice, if there are amino acids or lipids or anything that looks like the building blocks of biology, SUDA will find them. One grain, one flyby, one measurement could change the entire conversation about whether life exists anywhere other than Earth. Another instrument called REASON is an ice-penetrating radar designed to map the internal structure of the ice shell down to a depth of about 30 kilometers. For years, theoretical models have predicted that pockets of liquid water could be trapped within the ice shell itself, sandwiched between the frozen surface and the deep ocean below. If those lakes exist, REASON should detect them as bright radar reflections at shallow depths. And if they exist, it would mean Europa's habitable volume is not limited to the deep ocean. There could be water relatively close to the surface in smaller reservoirs that might be more accessible to future landers. The ocean itself is enormous. Current estimates put the depth at somewhere between 60 and 150 kilometers. Most models converge near 100 kilometers. For context, the deepest point in Earth's oceans, the Mariana Trench, bottoms out at about 11 kilometers. Europa's ocean could be more than 10 times deeper, contained inside a moon smaller than our own, and at the bottom of all that water sits a rocky seafloor. Not a layer of high-pressure ice like you find inside Ganymede, rock. Silicate minerals in direct contact with liquid water. Rock in contact with water matters because rock is where the minerals come from. Rock is where the chemistry starts. If the ocean floor is hydrothermally active, and there is good reason to think it is, then Europa has hot vents where mineral-rich water meets cold ocean, exactly the kind of environment where life originated on Earth nearly 4 billion years ago. The deep-sea vents on Earth, the black smokers and white smokers scattered along mid-ocean ridges, are some of the most biologically productive environments on the planet. They are teeming with life, not because they are warm, though they are, but because they provide chemical gradients that life can exploit for energy. Hydrogen sulfide, methane, iron, and other compounds dissolved in the vent fluid can be used by microbes as fuel. The microbes form the base of a food chain that supports entire ecosystems independent of sunlight. Europa's ocean has never seen sunlight. It has been sealed beneath ice for billions of years. If life exists there, it would have to be powered by chemistry, not photosynthesis. Hydrothermal vents are the most obvious energy source, but they are not the only one. Radiolysis, the breaking of water molecules by radiation, could also provide fuel. Jupiter's intense magnetic field channels high-energy particles into Europa's surface, splitting water ice into hydrogen and oxygen. Some of that oxygen could diffuse down through cracks in the ice and dissolve in the ocean, creating chemical disequilibria that life could exploit. The ocean does not need sunlight, it just needs chemistry. And chemistry happens wherever there is energy, water, and time. Enceladus, Saturn's sixth largest moon, has provided a proof of concept. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, discovered that Enceladus is venting plumes of water vapor, ice grains, and organic molecules from cracks in its south polar region. Cassini flew through the plumes multiple times and analyzed the material directly. The plumes contained salt, silica, and molecular hydrogen, all of which point to hydrothermal activity on the ocean floor. The hydrogen is particularly interesting because it is a byproduct of serpentinization, a chemical reaction between water and certain types of rock that releases hydrogen gas. On Earth, serpentinization is associated with hydrothermal systems that support microbial life. If the same process is happening on Enceladus, and the evidence suggests it is, then Enceladus has an active hydrothermal system. It has energy, it has chemistry, it has everything life needs except, possibly, time. Enceladus is much smaller than Europa, only about 300 miles across, and its ocean may not have existed for as long, but it is there, it is active, and it is accessible. The plumes are constant, predictable, and easy to sample. Enceladus is shouting its secrets into space. Europa is whispering them. Both moons are heated internally by tidal forces. Both have global oceans beneath ice shells. Both are in direct contact with rocky mantles. Both are chemically active. And both sit in the outer solar system, far from the Sun, in regions where traditional definitions of the habitable zone, the narrow band around a star where liquid water can exist on a planet's surface, do not apply. The habitable zone concept, as useful as it has been for exoplanet research, is too narrow. It assumes life needs sunlight. It assumes life needs a planet with an atmosphere. It assumes life needs to be on the surface. Europa and Enceladus demonstrate that none of those assumptions are necessary. Life, if it exists on these moons, would be living in darkness, in cold, in an environment that has never experienced a single ray of sunlight. And it would be doing just fine. Internal heat sources change the equation. Stars are not the only things that can keep a world warm. Radioactive decay, leftover heat from planetary formation, and tidal forces can all generate enough energy to melt ice and maintain liquid water for billions of years. This expands the definition of habitable worlds enormously. Every large moon in the outer solar system is a candidate. Ganymede, Callisto, Titan, Triton, possibly even Pluto's moon Charon. All of them could have subsurface oceans kept liquid by internal heat. All of them could, in theory, harbor life. The implications for astrobiology are staggering. If life can exist in Europa's ocean, if it can survive and thrive in an environment that has been sealed off from the sun for 4 billion years, then life is not as fragile or as rare as we thought. It does not need a star's warmth. It does not need an atmosphere. It does not need dry land. It just needs water, energy, and chemistry. And those three things are common. Water is the most abundant molecule in the universe after hydrogen and helium. Energy is everywhere, in the form of starlight, radioactivity, tidal forces, and chemical reactions. Chemistry happens wherever atoms meet. The ingredients for life are not rare, they are ubiquitous. What we do not know is whether life arises easily when those ingredients are present. Earth is the only data point we have, and drawing conclusions from a sample size of 1 is terrible science. Life on Earth appeared early. The oldest evidence for life dates back about 3.8 billion years, less than a billion years after the planet formed. That fast appearance suggests life arises readily when conditions are right, but it could also be a fluke, a single lucky accident that happened once and never repeated. Finding life on Europa or Enceladus or anywhere else in the solar system would answer that question, not completely, but definitively enough to shift the conversation. If life arose independently twice in the same solar system, then life is common. It is everywhere. The galaxy is full of it. And the search for intelligent life becomes a statistical inevitability rather than a hopeful guess. Even if we do not find life, the search itself is worth it. Europa's ocean is one of the most alien environments in the solar system, and we know almost nothing about it. We do not know its salinity. We do not know its temperature profile. We do not know how thick the ice is in most places. We do not know whether the ocean floor is smooth or fractured or covered in hydrothermal vents. We do not know if there are currents, if there is vertical mixing, if the chemistry is uniform or stratified. Every measurement Clipper makes will be the first of its kind. Every data point will refine our understanding of how icy moons work, how oceans evolve, and how heat and chemistry and structure interact in environments that have no analog on Earth. Clipper will not answer the life question. It is not designed to detect life directly. It is a reconnaissance mission, a scout. Its job is to map the terrain, identify the most interesting targets, and pave the way for future missions that could land on the surface, drill through the ice, and sample the ocean directly. NASA and the European Space Agency have both proposed follow-up missions, landers, ice-penetrating probes, submersible robots that could melt through the ice shell, drop into the ocean, and explore the seafloor. The technology is not ready yet. The mission architecture is not finalized, but the intent is there. Europa is too important to ignore. If there is life in that ocean, humanity will find it eventually. The warmth beneath Europa's ice is not an accident. It is not a fluke of orbital mechanics or a temporary condition that will fade in a few million years. Tidal heating is stable. As long as Europa remains in its current orbit, as long as Jupiter's gravity continues to flex the Moon's interior, the ocean will stay liquid. The system is self-regulating. If the ice shell thickens, insulating the ocean and trapping more heat, the interior warms and the ice melts from below. If the ice shell thins, allowing more heat to escape, the interior cools and the ocean freezes slightly, thickening the ice again. The equilibrium is stable over timescales of billions of years. Europa's ocean is not a transient feature. It is a permanent part of the Moon's structure. It has been there since shortly after Europa formed, and it will be there for billions of years into the future. That persistence matters for biology. Life, as far as we understand it, requires time. Time to evolve, time to adapt, time to develop the complexity we see in even the simplest single-celled organisms. 4 billion years is enough time, more than enough. If life arose on Earth within the first billion years, it could have done the same on Europa. The conditions are different, the chemistry is different, but the fundamentals are the same. Water, energy, carbon, time. Europa has all four. Michael Bland, a planetary scientist at the US Geological Survey, put it plainly in an interview with NASA. Of all locations in the solar system aside from Earth, Europa holds the highest potential for sustaining a habitable environment that could nurture microbial life. Not Mars, not Venus, not Titan, Europa, a frozen moon orbiting a gas giant 500 million miles from the Sun. That is where the smart money is. The discovery of carbon dioxide in Terra Regio is not proof of life. It is not even proof of habitability. It is one piece of evidence in a growing pile that suggests Europa's ocean is chemically active and connected to the surface. Carbon dioxide on its own is not enough to support life, but carbon dioxide plus water plus energy could be. The next step is to measure the other compounds in the ice: nitrogen, phosphorus, sulfur, the other elements life needs to build proteins, nucleic acids, and cell membranes. If those are present, and if they are in the right proportions, then Europa moves from interesting to urgent. The plumes are the key. If Clipper can fly through a plume and sample the material directly, it will get a snapshot of the ocean's chemistry without ever touching the surface. The plumes are sporadic, which makes them harder to predict, but Clipper will be watching. 49 flybys, 49 chances to catch a plume, 49 opportunities to sample material that left the ocean minutes or hours earlier. No other mission in the history of space exploration has had access like that. Cassini flew through Enceladus's plumes, but those flybys were not planned. They were opportunistic. Clipper is designed from the ground up to hunt plumes. If the plumes are active during Clipper's time at Jupiter, the mission will succeed. If they are not, the mission will still produce groundbreaking science, but the big prize, the direct ocean sample, will have to wait for another mission. Europa is not alone. The outer solar system is full of icy moons, and many of them probably have subsurface oceans. Ganymede, Jupiter's largest moon, has an ocean. Callisto might have one. Titan, Saturn's largest moon, has a subsurface ocean, though it is likely a water-ammonia mix rather than pure water. Triton, Neptune's largest moon, might have an ocean. Even Pluto, sitting at the edge of the solar system, shows signs of recent geological activity that could be driven by a subsurface ocean kept liquid by radioactive decay in its rocky core. The solar system is wetter than anyone expected. Not on the surface, where the cold and the vacuum freeze everything solid, but underneath, hidden, sealed beneath ice shells that protect the oceans from the harshness of space. These oceans are not curiosities, they are environments, habitats, worlds unto themselves, as large and as deep as Earth's oceans, existing in silence and darkness for billions of years, and they are warm, not from the sun, from within, from forces that have nothing to do with starlight and everything to do with gravity, friction, and the slow grinding of rock and ice. This is the lesson Europa teaches. Heat is not the exclusive domain of stars. Warmth does not require radiation from a fusion reactor 93 million miles away. Warmth can come from the inside, from the planet itself, from the moon itself, from forces that operate on timescales of billions of years and require no fuel except gravity and time. The sun is important. The sun powers life on Earth's surface, but the sun is not necessary. Not if you are willing to look beneath the ice. Not if you are willing to accept that life does not need light, does not need a blue sky, does not need anything except water, energy, and chemistry. And those things exist in the dark, in the cold, in places that have never seen a sunrise and never will. Europa is one of those places. A frozen moon, a hidden ocean, a world warmed from within. And possibly, just possibly, A world where life has been quietly evolving for 4 billion years, waiting for the day when curious primates from a planet 500 million miles away point their telescopes and their spacecraft in the right direction and ask the most important question humans have ever asked. Are we alone? Europa might have the answer. And in 7 years, when Clipper arrives, we will start to find out. Not all at once, not with a single dramatic revelation, but piece by piece, flyby by flyby, grain by grain. The ocean is waiting. The warmth is real, and the universe, it turns out, does not need fire to sustain life. Sometimes ice is enough, as long as there is something warm beneath it. And on Europa there is. Europa's ocean is hidden warmth in a frozen shell, but pull back far enough and Europa becomes a dot in the outer solar system, one small moon orbiting one massive planet, both of them bathed in a star field so dense you could count photons for a lifetime and never finish. Pull back farther and the solar system shrinks, the sun becomes a point, the planets vanish. Pull back farther still, and the Milky Way spreads across your view, a spiral of 400 billion stars, most of them burning at temperatures that would vaporize anything we recognize as matter, all of them radiating energy into a void that sits just 3 degrees above the coldest temperature the universe allows. Fire and ice, furnace and freezer. The two extremes sitting side by side, separated by nothing, coexisting in a way that should feel impossible, but is in fact the only way the universe knows how to operate. This is not a paradox. That is the lesson. That is the resolution. The sun does not warm space because space is not made of matter, and heat transfer requires matter. The vacuum does not conduct. It does not convect. It only radiates, and radiation does not warm the medium it passes through. The photons fly from the sun at the speed of light, carrying energy, indifferent to the emptiness they traverse, waiting for something solid to hit. When they find it, when they strike a planet or a moon or a spacecraft or your skin, the energy transfers, the molecules speed up, warmth appears, but the journey is cold. The space between the source and the target remains frozen, because the vacuum has no particles to absorb the energy, no temperature to raise, no mechanism to hold heat. The sun has been burning for 6 billion years, radiating 380 billion watts every second, and the void surrounding it has not warmed by a single degree. Not because the sun is weak, because the void is empty. And emptiness, by definition, has nothing to warm. That explanation resolves the immediate question, the surface-level confusion about why a 27 million degree furnace sits in the middle of a region that hovers 3 degrees above absolute zero. But it opens a deeper set of questions. Questions about where we fit in this picture. Questions about how fragile the conditions for life actually are. Questions about what it means to exist in a universe where the baseline state is so hostile to biology that the only reason anything survives anywhere is because of a narrow, improbable balance between fire and ice that took billions of years to stumble into and could be disrupted by 1,000 different mechanisms, some of them already in motion. Start with Earth. Our planet sits 93 million miles from the Sun. That distance is not arbitrary. It is not the result of random chance or divine preference. It is the outcome of gravitational dynamics that shaped the solar system over millions of years, pulling planets into stable orbits, ejecting some, capturing others, settling into a configuration that has remained mostly unchanged for more than 4 billion years. Earth ended up in the habitable zone, the Goldilocks zone, the narrow band around a star where temperatures allow liquid water to exist on the surface of a planet with an atmosphere. Too close and the water boils away. Too far and it freezes solid. Earth sits in the middle, just right, and that positioning is the only reason we are here to ask questions about it, but the margins are thin. Mercury orbits at 36 million miles from the Sun. The daytime temperature on Mercury's surface reaches 800 degrees Fahrenheit, hot enough to melt lead, hot enough to make the ground glow faintly in the infrared. Step into shadow and the temperature drops to negative 290 degrees Fahrenheit, a swing of more than 1,000 degrees depending on whether you are facing the Sun or not. Mercury has no atmosphere to moderate the extremes, no ocean to store heat, no mechanism to redistribute energy from the hot side to the cold side. The planet is a thermal gradient with a razor-thin twilight zone between furnace and freezer where the temperature might, for a brief moment, be survivable, but only barely and only if you are standing in exactly the right spot. Venus orbits at 67 million miles from the Sun, closer to Earth than Mercury is, but still well within what should be the habitable zone. Venus is roughly the same size as Earth, roughly the same mass, roughly the same composition. It should be Earth's twin. It is not. Venus has a runaway greenhouse effect. The atmosphere is 96% carbon dioxide, thick enough to create surface pressures 90 times higher than Earth's, hot enough to keep the surface temperature at 900 degrees Fahrenheit day and night, equator to poles forever. Lead melts on Venus. Zinc melts on Venus. The surface is hotter than Mercury despite being farther from the Sun because the atmosphere traps every photon that makes it to the ground and refuses to let the heat escape. The planet is a pressure cooker. Nothing we would recognize as life could survive there for more than a few seconds. Mars orbits at 142 million miles from the Sun, just outside the habitable zone by most definitions. Mars is cold. The average surface temperature is negative 80 degrees Fahrenheit. The atmosphere is thin, less than 1% the pressure of Earth's, mostly carbon dioxide with traces of nitrogen and argon. There is no liquid water on the surface. There are ice caps at the poles made of water ice and frozen carbon dioxide, and there is evidence that liquid water flowed on Mars billions of years ago when the atmosphere was thicker and the planet was warmer. But today Mars is a frozen desert. The thin atmosphere provides almost no insulation. The surface temperature swings wildly between day and night. A summer afternoon at the equator might reach 70 degrees Fahrenheit. A winter night at the poles drops to negative 200 degrees. Mars had a chance. It was warm once. It had water once. But it lost its atmosphere, probably stripped away by solar wind after the planet's magnetic field collapsed. And without the atmosphere, the water froze or evaporated into space. The planet died, slowly, quietly. And now it sits as a cautionary tale about how fragile habitability is. Earth avoided all of that. Earth kept its atmosphere. Earth kept its magnetic field. Earth kept its distance from the Sun in the narrow range where water stays liquid. Earth developed plate tectonics, a process that recycles carbon dioxide and regulates the planet's temperature over geological timescales. Earth had a moon, formed by a massive impact early in the planet's history, that stabilized the axial tilt and prevented the wild climate swings that would have made complex life impossible. Earth had liquid water for billions of years, long enough for chemistry to become biology, long enough for biology to become complexity, long enough for complexity to become consciousness. And all of it depended on a balance between the energy arriving from the Sun and the energy radiated back into space. Too much incoming energy and the planet overheats. Too little and it freezes. The balance has to be maintained constantly or the whole system collapses. That balance is not static. It shifts. The Sun's output has increased by about 30% since the planet formed. 4 billion years ago, the Sun was dimmer and Earth should have been frozen. It was not. The early atmosphere had higher concentrations of greenhouse gases, probably methane and carbon dioxide, which trapped enough heat to keep the surface warm despite the weaker sunlight. As the Sun brightened, life evolved to change the atmosphere, pumping oxygen into the air, reducing the greenhouse effect, and preventing the planet from overheating. The system regulated itself, not through conscious intent, through feedback loops, chemistry, biology, geology, all of it interacting, all of it balancing, all of it maintaining the narrow range of conditions where liquid water and carbon-based life could persist. The universe does not care whether life exists. The universe does not have preferences. It does not set the stage for biology and wait patiently for something interesting to happen. The universe operates on physics. Stars fuse hydrogen into helium and radiate energy. Planets orbit stars and intercept some of that energy. The energy warms the surface or it does not. Atmospheres form or they do not. Oceans appear or they do not. Life arises or it does not. The universe does not intervene. It does not adjust the dials to make things easier. The fact that Earth ended up with liquid water and a stable climate and an atmosphere that supports complex life is not evidence of design. It is evidence of statistics, billions of planets, trillions of stars, quadrillions of chances for the right conditions to align, and on this one planet, in this one solar system, in this one corner of an unremarkable galaxy, the conditions aligned. We are here not because the universe wanted us to be here. We are here because the physics allowed it and the chemistry stumbled into it and the timescales were long enough for the process to complete, and the margins are still thin. The habitable zone is not a wide, comfortable belt where everything is stable and safe. It is a knife edge. A few percent change in the Sun's output and Earth moves out of balance. A slight shift in the orbit, a change in the axial tilt, a disruption in the carbon cycle, and the whole system tips. There are feedback loops that stabilize the system. There are also feedback loops that destabilize it. Ice reflects sunlight. If the planet gets colder and more ice forms, more sunlight gets reflected and the planet gets even colder. That is a runaway feedback. It leads to snowball Earth events, periods in the planet's history when the entire surface froze over. The planet recovered from those events, but only because volcanic activity continued beneath the ice, releasing carbon dioxide into the atmosphere, trapping heat, melting the ice, and pulling the planet back out of the freeze. If the volcanoes had stopped, if the carbon cycle had broken, Earth might still be frozen today. The same thing works in reverse. If the planet gets warmer and ice melts, less sunlight gets reflected, and the planet gets even warmer. That is the runaway greenhouse effect, the process that turned Venus into an oven. Earth has not crossed that threshold yet, but it is not impossible. The right combination of factors, a brightening sun, a massive release of greenhouse gases, a disruption in the ocean currents that regulate heat distribution, and the planet could tip. Not quickly, not in a human lifetime, but over centuries or millennia, the balance could shift, and the conditions that allowed life to flourish could disappear. Life is fragile in that sense. It requires precise conditions, liquid water, stable temperatures, a source of energy, carbon chemistry, time. Take away any one of those, and the whole project stalls. The universe is not hostile to life in the sense that it actively opposes it. The universe is indifferent. It provides no guarantees, no safety nets, no second chances. If a planet loses its atmosphere, the universe does not replace it. If a star brightens too quickly, the universe does not dim it. If a civilization wipes itself out, the universe does not intervene. The conditions for life are rare, and the conditions for complex life are rarer still, and the conditions for intelligent life capable of asking questions about its own existence are so rare that we have exactly one example, one planet, one biosphere, one species capable of building telescopes and spacecraft and looking outward at the cosmos and realizing how improbable the whole situation is. But life is also resilient, microbial life especially. Bacteria and archaea have been found in every extreme environment on Earth. In boiling hot springs where the water is acidic enough to dissolve metal, in frozen Antarctic lakes buried under kilometers of ice, in deep ocean vents where the pressure is crushing and the water is superheated, in the dry valleys of the Atacama Desert where it has not rained in decades, in solid rock kilometers beneath the surface where the only energy source is radiation from radioactive decay, life finds a way. Not because it is clever or determined or blessed by some cosmic force, because chemistry is flexible and evolution is relentless. Given enough time, given enough chances, chemistry finds configurations that work, and those configurations persist because they are good at persisting. That is all life is, chemistry that figured out how to make more of itself. The extremophiles, the organisms that thrive in conditions that would kill most other life, are not oddities. They are proof that the range of habitable conditions is wider than we used to think. Life does not need a planet like Earth. It just needs liquid water, an energy source, and time. Europa has all three. Enceladus has all three. Titan might have all three. Mars might have had all three. The universe is full of places where the basic ingredients are present. Most of those places will never develop life. The chemistry will not find the right configuration. The conditions will change before the process completes. The timescales will not line up, but some of them will. Statistically, some of them have to. And if life can arise independently in multiple places in the same solar system, then life is common. Not intelligent life, not technological life, but life, microbial life, chemistry that replicates, chemistry that evolves, chemistry that persists. The question is not whether life exists elsewhere. The question is whether we will ever find it. The distances are staggering. The nearest star system, Alpha Centauri, is 437 light-years away. A light-year is the distance light travels in 1 year at 186,000 miles per second. It is roughly 6 trillion miles. Multiply that by 437 and you get the distance to the nearest stars. No spacecraft humanity has ever built can cover that distance in less than tens of thousands of years. Voyager 1, the farthest human-made object from Earth, is traveling at about 38,000 miles per hour. It has been flying for more than 45 years, and it has only just left the solar system. It will not reach the distance to Alpha Centauri for another 70,000 years. And Alpha Centauri is close. The Milky Way is 100,000 light-years across. The nearest large galaxy, Andromeda, is 5 million light-years away. The observable universe extends 93 billion light-years in every direction. The scale is incomprehensible. The distances are so large that even light, the fastest thing in the universe, takes billions of years to cross them. And the universe is cold. That is the baseline. The cosmic microwave background, the faint glow left over from the Big Bang, fills every cubic centimeter of space with radiation at 27 Kelvin, 3 degrees above absolute zero. That is the default state of the universe. Everything else, every star, every planet, every galaxy, every pocket of warmth, is a temporary deviation from that baseline. Stars burn for millions or billions of years, but eventually they run out of fuel. They collapse, explode, or fade into white dwarfs, neutron stars, or black holes. The energy they radiated spreads outward, diluting into the void, adding a negligible amount of heat to the cosmic background. The universe is expanding. The galaxies are moving apart. The distances are growing. And as the universe expands, the energy density drops, the temperature drops, the cosmic microwave background cools, slowly, over trillions of years. But inevitably, the universe is cooling down, and nothing can stop it. In the far future, trillions of years from now, the last stars will flicker out. The universe will be dark, cold, empty except for black holes, neutron stars, and the faint radiation field that continues to redshift and cool. Eventually, even the black holes will evaporate through Hawking radiation, a quantum process that allows black holes to lose mass over timescales so long they make the current age of the universe look like a rounding error. When the last black hole evaporates, the universe will be truly empty. No stars, no planets, no structure, just photons and particles spread so thin that the average distance between them is measured in light years. The temperature will be a fraction of a degree above absolute zero. The universe will have reached maximum entropy, heat death, not a dramatic explosion or collapse, just a slow fade into cold and dark and silence. That is the future. That is where the second law of thermodynamics leads. Entropy increases, order decreases, energy spreads out, the universe runs down. But that future is so far away that it is not worth worrying about. Trillions of years, quadrillions of years, numbers so large they lose meaning. The Sun has 5 billion years of fuel left. Earth has perhaps 1 billion years before the Sun brightens enough to boil the oceans. Humanity, if it survives, has time to explore, time to adapt, time to spread beyond this planet, beyond this solar system, beyond this galaxy if we figure out how. The universe is cold, and it is vast, and it is indifferent, but it is also full of energy, full of matter, full of possibilities, for now, for the foreseeable future, for the only timescales that matter to anyone currently alive. The cosmic dance between fire and ice is not a battle. It is not a struggle for dominance. It is a balance, a natural consequence of the laws of thermodynamics operating at every scale, from atoms to galaxies. Stars generate heat through fusion. Planets and moons absorb that heat through radiation. The vacuum between them remains cold because it has no particles to absorb the energy. The system is stable, not because it was designed to be stable, because the physics does not allow any other outcome. Energy radiates, space expands, temperature drops. That is the universe. That is how it has always worked. That is how it will always work until the end. And in the middle of all that, on a small rocky planet orbiting an average star in the outer arm of an average galaxy, chemistry became biology. Biology became complexity. Complexity became consciousness. Consciousness became curiosity. And curiosity built telescopes and spacecraft and looked outward at the fire and the ice and asked why. We are the universe asking questions about itself. We are the cosmos experiencing its own temperature. We are patterns of matter and energy that have organized themselves into configurations capable of reflection, capable of measurement, capable of standing on the surface of a planet bathed in starlight and wondering how any of this is possible. The answer is not simple. The answer involves quantum mechanics, general relativity, thermodynamics, chemistry, biology, geology, and a dozen other fields of study. The answer involves 13.8 billion years of cosmic history, the formation and collapse of countless stars, the assembly of heavy elements in supernova explosions, the condensation of gas clouds into planets, the delivery of water to Earth by comets and asteroids, the stabilization of the climate by feedback loops, the origin of life in some warm, shallow pool or deep ocean vent, the evolution of that life into forms that could survive and reproduce and adapt, the development of photosynthesis, the oxygenation of the atmosphere, the colonization of the land, the extinction events, the ice ages, the recoveries, the emergence of mammals, primates, hominids, humans. Every step in that chain required conditions that were improbable but not impossible. Every step depended on the balance between fire and ice holding long enough for the next step to occur. We are not the endpoint. We are not the goal. The universe does not have goals. We are one outcome among countless others, most of which never led anywhere, most of which ended in extinction or stagnation or collapse. But we are here. That is not trivial. That is not meaningless. We are the part of the universe that woke up. The part that looks outward and inward and asks questions about what it means to exist in a cosmos where the baseline state is hostile to everything we recognize as life, where warmth is temporary and rare, where the only reason anything survives is because a narrow, improbable set of conditions aligned and held long enough for chemistry to figure out how to persist. The paradox of the burning sun and the frozen vacuum is not a paradox. It is physics. The sun radiates. The vacuum does not absorb. The energy travels at the speed of light until it hits something. When it hits Earth, life happens. Not because the universe intended it, because the chemistry worked and the conditions were right and the planet stayed stable long enough for the process to complete. That is the resolution. That is the answer. And the answer is not comforting in the way religious or spiritual explanations are comforting. The answer does not tell you that you are special or loved or protected by cosmic forces. The answer tells you that you are a chemical reaction, a very complex, very persistent, very unlikely chemical reaction, but a chemical reaction nonetheless. And that reaction is happening right now, on this planet, in this solar system, in this brief moment between the Big Bang and heat death, when stars still burn and planets still orbit, and the temperature is high enough in a few rare places for liquid water to exist and for chemistry to become curious about itself. That is where we are. That is what we are. And the fact that we exist at all, that we are standing here asking questions about fire and ice and vacuum and heat, is the most improbable, most fragile, most extraordinary thing the universe has managed to produce. Not the stars. Stars are common. Not the planets. Planets are common. Not the galaxies. Galaxies are common. Us. Consciousness. The ability to measure the temperature of space and realize it is cold, to measure the temperature of stars and realize they are hot, and to understand why the two coexist without contradiction. That ability is rare. That ability might be unique. We do not know yet. We have not found anyone else. But whether we are alone or whether the universe is full of others like us, the fact remains. We are here. We are conscious. We are capable of understanding the cosmos, and that makes us, in a very real sense, the universe's way of knowing itself. The sun will keep burning. The vacuum will stay cold. The cosmic microwave background will continue to cool. The stars will eventually die. The galaxies will drift apart. The universe will fade. But for now, in this moment, on this planet, chemistry has become aware of the fire and the ice, and that awareness is writing these words, reading these words, asking whether there is more, whether there is meaning, whether the temporary warmth we experience on this tiny rock is enough. The universe does not answer, the universe does not speak, but the fire is still burning, the ice is still waiting. And between them, for now, we are here, That is not everything, but it is not nothing. It is the only thing we have, and it is, against all odds, enough. The Sun sits at the center of our solar system, a thermonuclear furnace burning at 27 million degrees Fahrenheit, and it has been pouring energy into the surrounding void for more than 4.5 billion years. The vacuum around it, the space through which that energy travels, remains at negative 454 degrees Fahrenheit, 3 degrees above absolute zero, the coldest natural temperature in the universe. That gap, that seemingly impossible contradiction, is not a flaw in the cosmos. It is the cosmos. It is the way heat works when there is nothing to heat. It is the way energy moves when there is no medium to carry it. And it is the only reason you are alive. Because radiation does not warm the vacuum it passes through. Because photons fly at the speed of light until they hit something. Because Earth intercepts a tiny fraction of the Sun's output and converts it into warmth, into weather, into oceans and forests and the chemical gradients that power every living thing on the surface. The vacuum does not care. The vacuum does not participate. It just lets the light through. And on the other end, 8 minutes later, warmth appears. Not because space is warm, because we are here to catch it. That is the lesson. Heat is not a blanket that spreads. It is a beam that travels. The universe does not meet you halfway. It does not cushion the extremes. It gives you fire and ice, furnace and void, and it leaves you to navigate the space between them. Life exists in that space, not because the universe intended it, because chemistry found a way, because planets formed at the right distances, because oceans stayed liquid long enough for something to stir. The margins are thin, the balance is fragile, but the balance is real. And for now, in this brief moment between the Big Bang and the heat death of everything, the light